Okay, welcome back to the last part of discussion, session 9. So far, we have talked about fuzzy implications, right? What they are, their definition, and a few examples. And we also talked about the three broad classes of fuzzy implications, namely SN implications, R implications, and QL implications, or I should say QL operations. And I made the point that our implications are very important. They are nice in the sense that they satisfy the left neutrality property. And in the last few videos, I also demonstrated at different points how using our implications can be beneficial. And then we talked about fuzzy propositions. There are four. These are those propositions that involve vague concepts. So Fatima is tall, room is warm, so on and so forth. And there are four broad categories of fuzzy propositions: two conditional, two unconditional, and both of them can be qualified or unqualified, right? And we talked about how to compute the truth values of those types of implications and uh, how to do inference with them when we have a conditional proposition. Namely, if we have a proposition of the form if x is a, then y is b, how do we infer an output b dash given an input a dash? And we also saw a method of truth value restriction that enables us to do this, the inference that I just talked about, in the setting of qualified conditional propositions. So something like if x is a, then y is b is very true. The final part is about fuzzy quantifiers, right? So this is the topic for this particular video. So notice that we have already talked about quantifiers in the setting of classical logic and set theory. So in the discussion session where I discussed fuzzy relations, I talked about quantifiers, right? And I talked specifically about existential quantifier, there exist, which is what this symbol stands for. And I also talked about universal quantification, uh, for all, which is what this symbol stands for. And as I mentioned at that time, that quantifiers essentially help define the applicability of predicates. So if I have a predicate, say p of x, that stands for x squared greater than 3, or a predicate of two variables x and n, standing for n greater than x, or for that matter, it could also be n equals to x plus 2n, and so on, right? You can have many examples of predicates. So quantifiers essentially help us define where these predicates are applied. So if I say that for every x, for every n p of xn, where the domain of quantification of this predicate is say real numbers, and the domain of quantification of this set is of this quantifier is um, say natural numbers, then we essentially are asserting when I write this that this predicate p of xn is applicable to real numbers and natural numbers. And more specifically, the first variable comes from the set of real numbers, and the second variable n comes from the set of natural numbers or positive integers, right? And similarly, I could have stated here that there exists x such that p of x, and say the domain of quantification of this quantifier is rational numbers, right? So, long story short, quantifiers help us define where a certain predicate applies. Okay. Now, whether that predicate is true or false in that quantified universe is another matter, but quantifies essentially indicates or it helps us define where a particular predicate applies. Okay. Now, existential quantifier and universal quantifier are examples of what are called as crisp quantifiers, right? Because when we say that there exists x such that p of x, there is no ambiguity when this this statement, this quantified statement is going to be true. It is going to be true if and only if we are able to find an x naught such that p of x naught is true, and it is true in no other case, right? Similarly, when I write something like p of x for every x p of x, we know exactly when this statement is true. There is no ambiguity regarding it. It's this statement is going to be true if and only if for each x coming from the domain of quantification, p of x is true, and it is, and this statement is not true in all the other cases, right? So that is why these two quantifiers, they exist and for all, are called as Crisp quantifiers because there is no ambiguity regarding their truth evaluation. Okay, but natural languages such as English or Tamil or Hindi, the languages that we speak, are full of imprecise or vague quantifiers. So what do I mean by that? So consider a sentence like number of tigers in India is around 300. So 300 tells us something about the quantity, but around 300, it's an example of imprecise quantification. We don't really know what it means to be around 3,500, right? So it could be 3,560, it could be 3,452, right? So what constitutes around 3,500 is not precise. It's not exact, right? So there is ambiguity involved. There is impreciseness involved, right? Similarly, if I say that almost half of the students in the class are girls, again, almost half is an example of imprecise quantifier or a vague quantifier, right? Because what constitutes almost half is not clear. If we have a class of, say, 10 students, then almost half can refer to 5. It could also refer to 4. It could also refer to 6. Again, there's imprecision involved. Similarly, when I say that approximately two-fifths of world's population has O plus blood group, again, there is imprecision. What constitutes approximately two-fifths? We don't have a precise answer to it, a precise answer to that question. So, uh, quantifiers like this, around 3,500, almost half, approximately two-fifths, these are quantifiers that help us make vague or imprecise assertions about quantity. And as a result, they are called as fuzzy quantifiers. Okay. Now, what fuzzy quantifiers translate to in mathematical terms? So when I say 3,500, there is no ambiguity involved. 3,500 is a specific number, and we know what that number is, right? However, when I say around 3,500, it's a vague concept, right? It's an imprecise concept, and we can model it as a fuzzy set. A fuzzy set that maybe look like this, right? So basically, a triangular fuzzy number like this. Okay. So the idea is that fuzzy quantifiers, which are essentially quantifiers that help us make imprecise assertions about quantity, like around 3,500, almost half, or approximately two-fifths, can be modeled as fuzzy numbers, right? So the way we mathematically deal with fuzzy quantifiers is through fuzzy numbers. Okay. Now, fuzzy quantifiers are of two types. The first type consists of quantifiers like around 3,500 or about 10 or much more than 100 or at least about 5, etc. Right? So these are number type quantifiers, right? Because you have a specific number and around that you have a quantification, right? So in a sense, the center of quantification is no. In this particular case, we have 3,500 as kind of the center, right? So center perhaps is not a very is not the right term to use here, But you get the point, right? Around 3500 means that we have a specific number, and around that number we are quantifying. Same is the case with about 10, right? So in other words, these are number type quantifiers, and these are also called as absolute quantifiers. Okay. And a characteristic of such quantifier is that you'll have a number there. You'll have a number that serves as the center around which quantification happens. Okay. And these quantifiers are modeled as fuzzy numbers over R. So around 3500 can be modeled as I said, 34 by the triangular fuzzy number 3400, 3500, and 3600. About 10 can be modeled by a trapezoidal number, say 7, 9, 11, 30, right? Much more than 100, uh, maybe, so maybe from, we have 100 here, and from 150, you have a linear increase to membership value 1, and say after 200, the membership value is 1, right? So any number greater than equal to 200 belongs to this vague concept much more than 100 to extent 1, and any number between 150 and 200, so there is it, it retains some membership value between 0 and 1 that is given by this line segment. Okay. So the point is that number type quantifiers, or what are called as absolute quantifiers, can be modeled as fuzzy numbers over real line, basically. The second type of quantifiers are exemplified by almost half, approximately two-fifths, most, or say few, and so on. Okay. So these are also called as relative quantifiers, and this type of quantifiers is concerned with the proportion. So what it means to be almost, so if suppose I say almost half of the students in the class are girls, right? So what it means to be almost half in a class of 10 students is different from what it means to be almost half in a class of say 300 students or 500 students and so on, right? So therefore, when I say almost half, I am actually making a statement about proportion. So what is the proportion of girls in the total number of students? So number of girls divided by total number of students. This proportion turns out to be around zero point 0.5, right? So that is what it means when I use the quantifier almost half. So quantifiers like this concern proportion. Similarly, when I say approximately two-fifths, say approximately two-fifths of the world's population has O plus blood group, then that means the size of the collection of people in the world that have O plus blood group divided by total number of people in this world, that turns out to be around approximately two-fifths, right? So second type of quantifiers, like almost half, approximately two-fifths, most, and few, these quantifiers have to do with proportion, and therefore they are called as relative quantifiers. And these quantifiers are modeled as fuzzy numbers over the unit interval, right? So maybe an almost half can be modeled. So half is essentially 5 by 10. Almost half can be modeled by a fuzzy number 3/10, 5/10, 7/10. So suppose the number of girls in a class is say 9, and the total number of students in the class is 20, then the proportion of girls in the class would be 9 by 20. And 9 by 20, this proportion belongs to the vague concept almost half to some membership, right? Maybe say zero point 0.8 or whatever, right? You can calculate that. So the point is, this relative quantifiers or proportion type quantifiers, examples of which are almost half and few and so on, They are modeled as fuzzy numbers over the unit interval. And I should be a bit careful here because when we define fuzzy numbers uh, in the first part of the course, by definition, a fuzzy number was defined to be a fuzzy set over the real line that has some interesting properties. Namely, it is normal and its alpha cuts are close and bounded intervals and so on. Right? Therefore, this phrase fuzzy numbers over unit interval is kind of it's not well defined because fuzzy numbers by definitions are fuzzy sets over the entire real line, right? So what I mean when I say fuzzy numbers over the unit interval is that the support of that number would be a subset of unit interval. So here, this is, for example, for almost when we model almost half as three, this triangular number, then its support is 3 by 10, comma 7 by 10. And that is a subset of unit interval. Okay. So I hope you got that nuance. Saying that fuzzy numbers over unit interval is a bit sloppy because fuzzy numbers by definitions are fuzzy sets over the real line. So when I say that fuzzy numbers over unit interval, what I mean is the support of that number is a subset of the unit interval. Okay. Anyway, so fuzzy quantifiers are those quantifiers that help us make imprecise or vague assertions about quantity. They are of two types. First types are number type quantifiers, like around 3,500, about 10, and so on. These are also called as absolute quantifiers, and they are modeled as fuzzy numbers over real line. Second type of quantifiers are proportion type of quantifiers, also called as relative quantifiers, like almost half, approximately two-fifths. And these are modeled as fuzzy numbers over unit interval. Okay. And a characterizing property of absolute quantifiers is that you will always have a number that serves as a center around which quantification happens. So in this case, that number is 3,500. In this case, you have 10 and so on. Okay. Now let us, this fuzzy quantifiers can appear in propositions, right? Those propositions can be crisp as well as fuzzy, right? So we'll start with crisp propositions with fuzzy quantifiers. So what is a crisp proposition? So it's a proposition that do not involve vague concepts, right? So for example, if I say that Narendra Modi was born on 17th September, there is nothing imprecise about this proposition. There are no vague concepts. We have Narendra Modi, who is a human being, and then we have a date, which is precise, right? There are no imprecise. There is no imprecision in this statement. If I had said that Narendra Modi is tall, then we would have a vague concept tall, and that would have meant that that proposition would not be crisp. Okay, so crisp propositions are those that do not involve any vague concepts. A couple of examples of crisp propositions are Narendra Modi was born on 17th September, and there are 365 days in a non-leap year. Again, there is no ambiguity or imprecision involved in this statement. Okay, now crisp proposition can involve fuzzy quantifiers. For example, I can say that at least about 10 employees in in the company are from Kashmir, or around 25 shops in the mall are clothing shops, or number of tigers in India is around 3,500, and so on, right? So in each of the case, we have a crisp proposition along with a fuzzy quantifier. In this case, the fuzzy quantifier is almost about 10. In this case, we have around 25. In third example, we have around 3,500 as the fuzzy quantifier. In the fourth and fifth example, these are the fuzzy quantifiers. And apart from that fuzzy quantifier, the rest of the proposition do not involve any vague concepts. Employees in the company that are from Kashmir, it's a crisp concept, right? Given a person, given an employee of the company, that employee is either going to be from Kashmir or he or she is not going to be from the Kashmir, right? So there is no ambiguity involved in these statements except for the quantifier, right? Okay, so the source of imprecision in crisp propositions with fuzzy quantifiers is fuzzy quantifiers only and nothing else, right? Now, such proposition, that is crisp propositions with fuzzy quantifiers, are of two basic types or two basic forms. The first form concerns absolute quantifiers, and the second form concerns relative quantifiers. So we will look at both these forms one by one. So let us start with the first form. So first form concerns absolute quantifiers. That is, in the first form, we will have absolute quantifiers. So a few examples of this first form are these three statements. At least about 10 employees in the company are from Kashmir. So at least about 10, it's an absolute quantifier, right? It's a number type quantifier, and we have a number 10 around which quantification happens. Similarly, the second statement has the fuzzy quantifier around 25, which is again a number type quantifier or an absolute quantifier. Similarly, in the third statement, we have the quantifier around 3500. That's again a number type quantifier, right? Or an absolute quantifier. Now, let us analyze these three statements, these three quantified propositions one by one, and try to identify the standard form, right? That all these three quantified propositions have. Okay. And in order to do that, given a quantified proposition, we'll ask two questions. In fact, we'll ask three questions. First one is what we are talking about. Second question would be what we are interested in. And the third question is what is the quantifier or what is the fuzzy quantifier, right? So given any crisp proposition with fuzzy quantifiers, when we analyze such a proposition, we ask three questions. What are we talking about? What we are interested in? And what is the fuzzy quantifier? So let us start with the first quantified proposition. At least about 10 employees in the company are from Kashmir. So what we are talking about in this proposition? We are talking about employees of the company. So our universe of discourse U is composed of employees of the company. That is, use the set of all employees in the company. The second question is what we are interested in. So we are interested in those employees of the company that are from Kashmir. So our set E becomes the set of all employees in the company, set of all employees of the company that are from Kashmir. The third question is what is the quantifier? The quantifier is at least about 10. So Q is at least about 10. So by asking these three questions, we arrive at a universe U, then we arrive at a set E, which is a subset of the universe, and it consists of all the objects in U that are of interest to us. Okay. And by answering the third question, we identify the quantifier Q. Okay. So given a crisp proposition that involve an absolute quantifier, we ask these three questions. And by answering these three questions, we arrive at U, E, and Q. Okay. And in this particular example, U was the set of all employees in the company. E was the set of all employees in the company that are from Kashmir. And Q, the quantifier, is at least about 10. So we can restate this proposition, this quantified proposition, in a manner where U, Q, and E becomes more apparent. Namely, we restate it like this. So there are about at least 10. So the quantifier comes first. There are at least about 10 Kashmiri employees in the company. Or in other words, there are QEs, where Q is the quantifier at least about 10, and E is the set of all employees of the company that are from Kashmir, or in other words, the set of Kashmiri employees in the company. So we started with this proposition, we identified U, Q, and E, and we note that this proposition can be expressed in this form. There are QEs, right? Or equivalently in this manner. There are at least about 10 Kashmiri employees in the company. Okay. Let us look at the next example. Around 25 shops are in the mall. Around 25 shops in the mall are clothing shops. So what we are talking about? We are talking about shops in the mall, right? So U, our universe of discourse, is the set of all shops in the mall. And what we are interested in? We are interested in those shops that sell clothes, or in other words, those shops that are clothing shops. And therefore, our set E would be the set of all clothing shops in the mall. And what is the quantifier here? It is around 25. So Q is around 25. Okay. Again, we can restate this proposition, this quantified proposition in a manner where U, Q, and E become much more apparent, namely in this form. There are around 25 clothing shops in the mall, or in other words, there are QEs. Q standing for this, and E standing for this, clothing shops in the mall. Okay, let us look at next example. Number of tigers in India is around 3,500. What we are talking about? We are talking about tigers in India. So what will be our universe of discourse? U. It will be the set of all tigers in India. And what we are interested in. Now, this is a nice example, right? Because in this particular proposition, we are interested in tigers in India, right? And that is precisely our set U. In the last two examples, we have a universe of discourse. In the first example, that universe of discourse was the set of all employees of the company. In the second example, our universe of discourse U was the set of all shops in the mall. And the proposition we had asserted something about a part of that universe of discourse. The first proposition talked about that part of the universe, namely part of the employees of the set of employees of the company that are from Kashmir. Similarly, the second proposition talked about the part of the universe, namely the universe, namely the clothing shops in the mall, right? Which is a collection, which is a sub collection of the set of all shops in the mall. This third example is somewhat different in the sense that what we are interested in is the entire universe U. So what we are talking about and what we are interested in are essentially the same. In other words, E is equal to U. Okay, so I hope you got this nuance. In the previous two examples, we had in all the quantified proposition, we'll have a universe of discourse U. It would consist of all the objects that we are talking about. And generally, the proposition that we have would say something about a part of that universe. In the first example, we had Kashmiri employees. In the second example, we had clothing shops. However, in this particular example, EU happened to be Q. So we are talking about all, so our set of interest E is the entire universe of discourse U. Okay. So it is useful to recognize this, right? So that you don't get confused when you actually encounter questions on this topic. And what is the quantifier? Pretty straightforward, around 3,500. Again, we can restate this proposition in a manner where Q, E, and U, Q, and U, E, and Q become more apparent. Namely, there are around 35 tigers in India, 3,500 tigers in India, where around 3,500 is our quantifier Q, and tigers in India is E. Okay. So I hope I have convinced you by now that the standard form of propositions that we have been talking so far, or the canonical form of propositions that we have been talking so far, is there are QEs, where Q is some absolute quantifier. In the first example, it was about at least about 10. In the second example, it was around 25. And in the third example, it was around 3,500. So Q is an absolute quantifier, and E is the subset of universe U that interests us, or basically that the proposition P proposition talks about. The proposition P says something about. Okay, so I hope that is clear by now. In the first example, Q was at least about 10, and E was the set of all employees in the company that are from Kashmir. In the second example, Q was around 25, and E was the set of all clothing shops. In the third example, Q was around 3,500, and E was the set of all tigers in India. Okay, so the canonical form of the first canonical form, right? Or basically the canonical form of crisp propositions with absolute quantifiers is this. Involving absolute quantity. So this is the canonical form of crisp propositions involving absolute quantifier. There are QEs. Okay. Now the next natural question is, how do I compute the truth value of such propositions? Okay. Now let us go back to this example. We can we can E is our set of all employees in the company that are from Kashmir. We can find the set of this size. Now we can find the size of this set E. Namely, we can compute the cardinality of E. And having computed the cardinality of E, say this E turns out to consist of, I don't know, 11 employees. Okay, or maybe 9 employees or 8 employees, anything. Having computed this size of set E, to find out how true this proposition how true this proposition is, it suffices to check, or it suffices to find out to what extent this number, this size, belongs to the quantifier Q. Okay, so take a moment to recognize what I've said. Q here is the quantifier at least about 10, right? This proposition says that there are at least about 10 Kashmiri employees in the company, and therefore our quantifier Q is this. And we find out the set of all Kashmiri employees in the company. That is, we find the size of set. We specify the set E, and then we find out its size. Okay, and therefore the degree to which this size belongs to this concept, at least about 10, this vague concept, at least about 10, tells me to what extent this proposition is true. So if the number of Kashmiri employees in the company is say 5, then it is intuitive to say that this proposition should not be true to a very high degree, right? Because 5 is very incompatible with the vague concept at least about 10. Or however, but if the number of Kashmiri employees in the company is say 12, then 12 is definitely compatible with at least about 10, right? It is definitely greater than equal to 10, and therefore it is perfectly compatible with this vague concept. So in other words, when we have figured out that the canonical form of crisp propositions involving absolute quantifier is this, there are QEs. In order to compute its truth value, we find the set of size E, that is how big the subset of universe U that interests us is, and then we simply find out to what extent or what is the membership value of this size in the quantifier Q, in the fuzzy quantifier Q. Okay. So what is the truth value of this proposition? It's membership of cardinality of E in Q. Now notice that Q is a absolute quantifier in this case. More generally, it's a fuzzy quantifier, and therefore it is going to be either a fuzzy number over the it's going to be a fuzzy number over the real line, or in general, it's going to be a fuzzy set over the real line. And therefore, I should have written this, right? Because Q is the symbol we are using for the fuzzy set, right? For a particular kind of fuzzy set that is this particular fuzzy quantifier Q. Therefore, the more appropriate way of writing the truth value of proposition P is that it's the membership of mod E, that is cardinality of E in Q, which is what this symbol denotes. But I'm going to use this notation because because it generally emphasizes the quantifier, right? So this is what I like to use. But if this notation is making you uncomfortable, use the proper notation by all means. Okay. Okay. So let us again go back to the first example, right? And just a minute. Now, suppose the set of size E is 9. That is, there are 9 Kashmiri employees in the company. Then how do you find the truth value of this proposition? So, first of all, we need to decide what is the membership function of this quantifier, at least about 10. So, so at least about 10. So, about 10 can be represented by a quantifier like this: 8, 10, 12. Okay. Now we are saying that at least about 10. So, if you have a number that is greater than equal to 10, then that definitely satisfies, then that would satisfy at least about 10 to a degree 1, right? What I mean to say is the following. It makes sense to use triangular number 8, 10, and 12 to represent the wave concept about 10. And from about 10, I want to go to the fuzzy set is that can represent the wave concept at least about 10. Okay. Now about 10, it is easy to define a appropriate fuzzy set for about 10, namely 8, 10, and 12. Now let us focus on at least about 10. Any number that is greater than or equal to 10 would satisfy this concept at least about 10 to membership 1, right? In other words, for any number greater than or equal to 10, the membership of that number to the wave concept at least about 10 would be 1. So we'll have a membership value 1. And as the number starts moving away from 10 in the left direction, or in other words, as you start considering numbers that are smaller than 10, its membership in the concept at least about 10 would decrease, right? Because at least 10 means that we are interested in the property of being greater than equal to 10 in some vague manner. Okay. So in other words, this will be the fuzzy set corresponding to the concept at least about 10. I hope it is clear. About 10, fairly straightforward to deal with. Then we look at least about 10. Now, any number that is greater than equal to 10 would definitely satisfy this way concept to degree 1. And therefore, we have this part. And as you move away from 10 in the left direction, that is, as you start considering numbers smaller than 10, its membership to this way concept at least about 10 would start decreasing. So it makes sense to take something like this. Okay. Of course, you could have taken, instead of 8 and 12, you could have used 7 or 13 or 9 or 11. That is up to you. But the general shape is this. Okay. So suppose I model my at least about 10 like this. Okay. And now we are given that mod of E, that is cardinality of E is 9. And therefore, the truth value of this proposition is Q of mod E, or in other words, Q of 9. And Q here, Q is how this is how the Q looks like. So what is Q of 9? So 9 lies between 8 and 10. So somewhere here. So this is the membership value. This is the membership value. And how do we compute that membership value? It is T minus 8 divided by 10 minus 8 at T equals to 9. So 9 minus 8 divided by 2, or 1.5. Okay. Now, generally in questions, you would be given the fuzzy set corresponding to the quantifier. In this particular example, I constructed the fuzzy set by myself because I wanted to give you a sense of how one can go about constructing appropriate fuzzy sets for fuzzy quantifiers. Okay. So let us now come to the second example. There are around 25 clothing shops in the mall. Again, the canonical form is there are QEs, where Q is the quantifier around 25 and E is the set of all clothing shops in the mall. That is the subset of universe U that interests us. And suppose that it is given that there are 27 clothing shops in the mall. That is mod of E, or in other words, cardinality of E is 27. Then how do we compute the truth value of this proposition? It would be Q of mod E, or in other words, Q of 27, where Q is the quantifier around 25. Now, around 25 can be modeled like this. So maybe 24, 26, and then 28, 22. Maybe by this trapezoidal fuzzy number. Okay, makes sense? So between 24 and 26, any number between 24 and 26 satisfies the wake concept around 27 to degree 1. And between 20 and from 24, from 22 to 24, the membership of a number to the wake concept around 27 increases linearly. And from 26 to 28, the membership of a number in this wake concept around 27 decreases linearly. And for any number greater than 28 and less than 22, the membership of that number in this wake concept is zero. Okay. So what is Q of 27? 27 lies between 26 and 28. So we have to basically find out what is the value of, we have to basically consider this line segment. So what is the equation of that line segment? It's 28 minus t divided by 28 minus 26. And this has to be computed at t equals to 27. This again is half and therefore 0.5. Okay. Now let us consider the final example. There are around 3,500 tigers in India. Again, the canonical form is there are QEs, where Q is the quantifier around 3,500. Suppose I represent it by a triangular number 3,200, 3,500, 3,800. And given that there are 3,682 tigers in India, that is the cardinality of is 300, 3,682. The truth value of this proposition would be Q of 3,682. Now, 3,682 lies between 3,500 and 3,800. So therefore, this value would be right. And what is this quantity? This quantity is 118 by 300. And if you evaluate it, you get 0.39. Okay. Now, as I said earlier, when you are given a question on crisp propositions with fuzzy quantifiers, the quant or that matter for any question, any on quantified proposition, the fuzzy set corresponding to the quantified would be specified. But in when we are actually applying fuzzy set theory in real world, in practical applications, we are the ones who have to decide what is the appropriate fuzzy set for the quantifier that we are dealing with, right? And it is useful to recognize that the fuzzy set that is used, or basically the fuzzy number that are used to represent the quantifier, the parameters of those fuzzy numbers. So in this case, uh, we are dealing with the quantifier around 3,500. So the center of quantification is 3,500. So it makes sense to use a triangular number or a trapezoidal number. So the middle of that number is 3,500, and that is clear from the quantifier itself. But what are the left and right extreme? Or in other words, what are these two parameters, A and C? Now, I could have taken A to be 3,300 or A to be 3,400 or C to be, I don't know, 4,000. So again, that depends upon the context, right? And it is such a fuzzy set is generally constructed by an expert. Okay. So it is useful to know that, right? When you are actually applying fuzzy set theory in real life applications, you have to design a number of fuzzy sets, and consequently, you have to design fuzzy numbers corresponding to fuzzy quantifiers. And in such cases, an expert is generally appointed to do that. Okay, so we are done with the first form. That is, we are done with the crisp propositions that involve absolute quantifiers. Let us now look at the second form, which has to do with relative quantifiers. A couple of examples of crisp propositions with relative quantifiers are as follows. Almost half of the students in the class are girls, or approximately two-fifths of world population has O plus blood group. Let's start with the first example. Almost half of the students in the class are girls. What we are talking about? We are talking about students in the class. Therefore, U becomes the set of all students in the class. What we are interested in? We are interested in those students who happen to be girls, and therefore our set E will be the set of all students in the class who are girls. And what is the quantifier here? It's almost half. Therefore, Q is almost half. Now, again, I can restate this proposition in a manner where U, E, and Q become more evident, namely like this. Among students in the class, there are almost half who are girls. So we first specify our universe of discourse, that is among U's in U, among U's in set U. So U is the set of all students in the class. So for U in U, among U in U essentially translates to among students in the class. That is this part. And secondly, we specify the quantifier and the set that interests us. So there are almost half. Almost half is our fuzzy quantifier Q, and who are girls. This is our set E that interests us. All right. So for this example, almost half of the students in the class are girls. U is the set of students in the class. E is the set of all students in the class who are girls, and our quantifier Q is almost half. And we are able to express this proposition in this manner. Among students in the class, there are almost half who are girls, or in other words, among U's in set U, there are QEs. Let us look at the next example. Approximately two-fifths of the world's population has O plus blood group. What we are talking about? We are talking about people in the world. So U, so world's population, right? So it's world's population. By world's population, we essentially mean the set of people in this world, right? Because the population is constituted by people living on this planet, in this world. Therefore, our set E is the set of all people in the world. What we are interested in? We are interested in those people who happen to have O plus blood group. Therefore, our set E will be the set of all people who have O plus blood group. And what is the quantifier Q? It's approximately two-fifths. Again, we can restate this proposition in a manner where U, E, and Q become more evident, namely like this. Among people in the world, there are approximately two-fifths. So this is our proposition Q who have O plus blood group. So this is our E. And this is basically among people in the world, among U's in set U. The, the function of this part is to tell you what is the universe. Okay. So I hope I am able to convince you by now that the canonical form of crisp proposition that involve relative quantifiers is this. Among U's in set U, there are QEs, where Q is a relative quantifier. In the first case, it was almost half. In the second case, it was approximately two-fifths. E is the subset of the universe that interests us. In the first case, it was the set of all students in the class who are girls. In the second case, is the set of all people in the world that happen to have O plus blood group, right? And among U's in U, basically help us identify the universe, the underlying universe. Okay. In some cases, in some books, you will see that they define the canonical form as simply there are QEs. That is also okay, but I prefer to have this notation because it helps us make the it basically makes clear what is the universe U. And the reason why I'm doing that will become evident in a short while. Okay. So this is the canonical form. Now the question is how do we compute the truth value of this proposition? So again, going back to the first example, almost half of the student in the girls. U is the set of all student in the class. Okay. So the size of our universe is mod U. What we are interested in is those students who are girls. That is set E. We can also find the size of set E, namely the cardinality of set E, or in other words, mod E. Now this ratio mod E by mod U tells you what proportion of student in the class are girls. That will give you some number in the unit interval. And we can find the membership of this proportion in the vague concept almost half. This vague concept almost half is represented by fuzzy set E, fuzzy set Q, right? The fuzzy quantifier Q. We can find the membership of this proportion mod E by mod Q, or in other words, proportion of girl students in the class. And then I can check what is the membership of this proportion in the fuzzy set almost half. And that will give me a number that serves as the truth value of this proposition. So if there are, say, 100 students in the class, that is mod 100, mod U is 100, and suppose number of girl students is 56. And in the second case, the number of girl student is 22. So this proportion mod E by mod Q tells me, this ratio mod E by mod Q tells me the proportion of girl students in the class. In this particular case, that proportion is very small. And therefore, intuitively, in this particular case, when number of girl students is 22, this proposition, this quantified proposition, almost half of the student in the class are girls, should be true to a small degree. However, in this case, we have proportion as 0.56, right? And this proportion is more compatible with the vague concept almost half. And therefore, the truth value of this proposition in the case when mod is 56 should be high, right? So I hope I am able to make you recognize that computing this proportion mod e by mod q, mod e by mod u, and then computing its membership in the fuzzy set of the quantifier, the fuzzy set that represents the quantifier q, essentially gives you the truth value of this proposition. Okay. So in other words, the truth value of propositions of crisp proposition involving relative quantifiers, the canonical form of which is this, the truth value of such proposition is given by mod E by mod U. Okay. This is a this proposition, we have relative quantifiers at play, and therefore proportion is what matters. Proportion of girl students in the class or proportion of people in the world who happen to have O plus blood group. And having computed that proportion, that ratio, mod D by mod Q, I simply check to what extent that ratio or that proportion belongs to the fuzzy set corresponding to the quantified Q. And that is enough to give us, and that is what gives us the truth value of this proposition P. Okay. And this is the reason why I prefer to have among U's in set U, there are QEs instead of just there are QEs. Because in truth value computation, you have to take mod Q. So it is useful to have among U's in set U in the canonical form itself to remind us that we are dealing with a particular universe U. Okay. But if you are someone who wants to follow book, the book, and by book I mean the Yuan and Claire's book, which has been suggested in the first discussion session and on the course page as well. So if you want to follow that book verbatim, then you can use this canonical form as well. The point is, this is how the truth value of crisp proposition with relative quantifiers is computed. Now, okay, let us consider the first example that we discussed. Among students in the class, there are almost half who are girls. That is, almost half of the students in the class are girls. Suppose there are 50 students in the class and there are 22 girl students. Then what will be the truth value? It will be 22 by 50. Now, what the fuzzy set corresponding to the fuzzy this quantifier, relative quantifier, almost half is not given to us. So we'll construct it by ourselves. So almost half is 1 by 2, so 5 by 10. So we start by considering this unit interval, and suppose I divide it into 10 parts. Okay. Now 5 by 10 lies here. and we are interested in almost half, right? So maybe we can use a triangular fuzzy number. So that is, we can model almost half by a triangular fuzzy number 3 by 10, 5 by 10, 7 by 10. That is when the proportion of girl student in the class is between 5 by 10 and 7 by 10, that is one half and point 0.5 and point 0.7. The membership lies on this. And when the proportion of girls student in the class is between point 0.3 and point 0.5, membership lies on this. And if the proportion of girls happen to be, say, point 0.2, that is uh, point 0.2, then in such a case, and then in such a situation, that proportion, again, intuitively speaking, if the proportion of girls in the class is point 0.2, then that means it is certainly not true that we have almost half girl students in the class, right? Because point 0.2 is not at all compatible with the wake concept almost half. Okay, so I hope you are able to see that. So suppose I use this fuzzy set to model my quantifier almost half, relative quantifier almost half. Then what will be the truth value? So I have to compare. I have to decide where 22 by 50 lies. So maybe it is useful to have the denominator as 10. So 22 by 5 by 10, right? This is same as this. And 22 by 5 is 4.4. So 22 by 50 is nothing but 4.4 divided by 10. And 4.4 by 10 lies between 3 by 10 and 5 by 10, right? So basically, 5 by 10 minus 3 by 10. We have to evaluate this at 4.5 divided by 10. So this turns out to be equal to 4.4 minus 3 divided by 2, or in other words, 1.4 divided by 2, or in other words, zero point 0.7. So the truth value of this is zero point 0.7 if we assume, if we model our relative quantifier almost half like this. Okay, let us do the next question. Here we have quantifier Q to be approximately 2/5. Suppose I model 2/5 as, so 2/5 is 4 by 10, right? So it makes sense to model this as, say, 2 by 10, 4 by 10, and 6 by 10. So the strategy that I have adopted when I was constructing a fuzzy set for almost half, and in this case, approximately 2/5, is that I divide the unit interval into 10 parts. So 1 by 10, 2 by 10, 3 by 10, 0, 1 by 10, 2 by 10, 3 by 10, all the way to 9 by 10 and 10 by 10, that is 1. And then I locate my I locate that part of this unit interval where the membership value of any of a proportion would be 1. So in the previous example, almost half of the student in the girls, almost half of the students in the class are girls. And suppose the class has 50 students. Now, if the number of girls happen to be 25, then this we have uh, exactly half of the student in the class are girls, and therefore, in such a case, um, this proposition would be true to degree 1, or in other words, a proportion of 1 by 2 at a proportion at a proportion 1 by 2, the membership to this fuzzy set almost half should be 1. Or in other words, the proportion at a proportion 5 by 10, the membership to the fuzzy set almost half should be 1, right? So I locate the point at which the membership is 1. In this case, it's 5 by 10. And then and then I basically construct a triangular number around with the center as 5 by 10. So 3 by 10 and 7 by 10. So that's a useful strategy to construct um, fuzzy sets corresponding to relative quantifiers. In this case, we have 2/5. So if there are exactly two-fifth of world population happen to have O plus blood group, then this proposition would be exactly true. That is, its truth value will be 1. Therefore, a proportion of exactly two-fifth, that is 2 by 5, may would belong to the fuzzy set corresponding to quantified Q to membership 1. So 2/5 is 4 by 10. Therefore, use 4 by 10 as the center for my fuzzy set that is supposed to represent my quantified Q. And then I construct a triangular number around it. I could have constructed a trapezoidal number as well. Again, I'm just laying down a particular strategy. You can come up with other strategies as well. So the point is selecting this as the fuzzy set for almost half and this as the fuzzy set for approximately 2/5 is meaningful. It makes sense. Okay. Now, so we know that suppose there are, oh, sorry, numbers are swapped here. Now, we know that there are roughly 8.2 billion people in the world, and I did a Google search to figure out that approximately 3.075 billion people have uh, O plus blood group. So that's why I've taken these particular numbers. Now, given these numbers, we can find the truth value of this proposition P, and that is basically Q of mod E by mod Q, or in other words, Q of 3.075 billion divided by 8.2 billion. Billion and billion would cancel out. So we'll have this. Right now, I have to compare this ratio with these numbers, right, to identify where exactly this lies. So I would make sure that the denominator is 10, and this quantity 3.075 divided by 8 by 2 and multiplied by 10, this turns out to be equal to 3.75, right? So we are evaluating Q of 3.75 by 10. So 3.75 lie between 3.75 by 10 lies between 2 by 10 and 4 by 10. And therefore, Q of this quantity would be and therefore we get this, or in other words, 1.75 by 2, right? Or in other words, 0.875. So the truth value of this proposition is 0.875 if we use this fuzzy set to model the relative quantifier approximately 2/5. Okay, so we are done with crisp proposition with fuzzy quantifiers. Now we can also have the case where fuzzy propositions involve fuzzy quantifiers. So maybe statements of this form. Approximately 50 staff members in the college are middle-aged. Approximately 50, it's a fuzzy quantifier, right? And staff members in the college that are middle-aged. So middle-aged is a vague concept, right? It is not the case that someone is exactly middle-aged or someone is not middle-aged, right? Uh, People are middle-aged to different degrees, and therefore we have a vague concept, and therefore this we have a fuzzy proposition, and we also have a fuzzy quantifier approximately 50. Similarly, in the second example, there is a fuzzy quantifier about 50, and we also have a vague concept, namely the vague concept of fluency in English language. Again, it does not make sense to say that someone is exactly fluent in English or someone is not fluent in English. People are fluent in the English language to different degrees, and therefore we have a vague concept along with a fuzzy quantifier. Similarly, in the third example, we have a vague quantifier about 10, and we have two vague concepts. First vague concept is fluency in English language or high fluency in English language, and the second vague concept is young. Similarly, in the fourth example, we have a fuzzy quantifier close to 50, and we have two vague concepts, namely tall and underweight. Tall patients and underweight patients. Similarly, in the last two examples, we have relative quantifiers, so few, almost all. So in the first four examples, we have absolute quantifiers. We have number type quantifiers, approximately 50, about 15, about 10, close to 85. These are examples of number type quantifiers, or in other words, absolute quantifiers. In the last two examples, you have relative quantifiers, and you also have vague concepts, so tall, overweight, and so on. So as of now, till now, we dealt in the previous slides, we dealt with crisp propositions involving fuzzy quantifiers. Now, it can be the case that you have a fuzzy proposition with a fuzzy quantifier. These are six examples of such propositions. Now the question is, how do we deal with such quantified propositions? So first of all, recognize that in these six propositions, that is in fuzzy propositions involving fuzzy quantifiers, the source of impreciseness is twofold. First one is you have a vague quantifier, you have a fuzzy quantifier, and that is one source of imprecision. And the second source of imprecision is the vague concepts themselves. So in the first, you have middle aged. In the second example, you have high fluency in English. In the third example, you have high fluency in English as well as young. Right? So in fuzzy propositions involving fuzzy quantifiers, you have two sources of imprecision, namely fuzzy quantifiers and vague concepts. Okay. Now, fuzzy quantifiers can involve absolute quantifiers, as we just saw, or they can involve relative quantifiers, right? And fuzzy propositions involving absolute quantifiers turns out to be of two basic forms, right? So we start by discussing the first form. So examples of fuzzy propositions involving first form of fuzzy quantifiers with okay, first form of fuzzy propositions with absolute quantifiers. First form of fuzzy propositions with absolute quantifiers. So these are two examples of such a form. Approximately 50 staff members in the college are middle-aged. There are about 15 students in the class whose fluency in English is high. So we start by analyzing these two quantified propositions. Again, we'll ask ourselves a certain questions. First question would be, what we are talking about. Second question is, what we are interested in. Third is, and we will see that this question, the second question, will lead to will lead to a set of two answers. Okay. And the third is, of course, what is the quantifier? So we'll ask ourselves these three questions whenever we are, as I have already mentioned, whenever we are dealing with quantified propositions, these are the three questions that we need to ask ourselves. Okay. So let us start. Approximately 50 staff members in the college are middle aged. So what we are talking about? We are talking about staff members in the college. Therefore, our universe of discourse U would be the set of all staff members in the college. What we are interested in? We are interested in those staff members that are middle aged. In other words, we are interested in the age of staff members, right? And therefore, we define a variable V to be the age variable. And for each staff member U, this variable takes a value V of U, giving me the age of staff member U. Then we have a vague concept middle aged, right? And that vague concept is modeled by a fuzzy set F over the set of values of variable V. Namely, recall variable V is the age variable. It takes certain values, right? So for age variable, the set of values could be 0 to 100, right? And F is a fuzzy set over this set of values that the variable V take. And this fuzzy set F models the vague concept middle-aged. And lastly, what is the fuzzy quantifier? Approximately 50, right? I hope that is clear. By asking the question what we are talking about, we identify the universe of discourse U. By asking ourselves what we are interested in, we identify the variable v, and the fuzzy set f. And by asking ourselves what is our quantified, we identify our quantified q. Okay. So in fuzzy propositions involving quantifiers, the analysis led by these three questions lead us to identify a universe of discourse, a variable, a fuzzy set f, and a quantifier. Okay. Now I can restate this fuzzy proposition in a manner where these three parameters are much more evident. Namely, in this manner, there are approximately 50 staff members in the college such that their age is in the middle, or that is their middle age. So, in other words, there are QUs in set U. Q here is the quantifier approximately 50. U's in set U stands for staff members in the college such that their age is in the middle. Age is captured by the variable V. Variable V is the age variable. V of U stands for variable of staff member U. Is F in the middle. So basically such that their age is captured by V, in the middle is captured by F. So in other words, we started with a quantified proposition. Approximately 50 staff members in the college are middle-aged. We asked ourselves these three questions, and that led us for that helped us identify the universe of discourse U, the parameter, the variable V that captures what we are interested in, the vague concept being modeled by fuzzy set F, and the quantifier Q. And we can restate our proposition in a manner where these parameters Q, V, F, U, V, F, and Q becomes more evident, namely in this manner, right? Now let us look at the second proposition. There are about 15 students in the class whose fluency in English is high. So what we are talking about? We are talking about students in the class. So our universe of discourse would be the set of all students in the class. Now what we are interested in? We are interested in fluency of students in the English language, right? So we define a variable v, which for each student u tells me how fluent u is by a number v of u. In other words, the variable v is the fluency variable. It takes some values. Maybe we can. It takes values in the set 1, 2, all the way to 10, where 1 denotes low fluent, extremely low fluent, the fluency, the most basic, the most lowest level of fluency you can have, and 10 means it's the highest level of fluency, right? So this variable v is the fluency variable, which for each student u takes a value v of u, telling us how fluent the student u is, right? And namely, we are interested in fluency of students in the English language, namely the high fluency of the students in the English language. So we have a vague concept high, and that is modeled by a fuzzy set f over the set of values that the variable v can take. And this fuzzy set f models the vague concept high fluency. So f here would be a fuzzy set over this set 1 to all the way to 10, right? So this, because this is the set of values that the variable v, the fluency variable v takes. And what is the quantifier q? It's about 20, about 15, right? So this is our q. So we have identified our universe of discourse. Then we asked ourselves what we are interested in, and answering that question helped us identify the relevant variable v and the fuzzy set f. And then we finally asked ourselves what is the quantifier q, and we answered that question. So we answered that question also, right? Now we can restate this proposition in a manner where u, v, f, and q become more apparent, namely like this. There are about 15 students in the class such that their fluency in English is high. When I state my proposition, the same proposition in this manner, then this quantifier q becomes evident. U in use, so basically student in the class, such that V is F, right? So there are Q U's in set U such that V U is F. Here Q is about 15. U's in set U essentially stands for student in the class. V of U stands for fluency in English. F stands for high, right? So this proposition that we started with, that involved, that is a fuzzy proposition with a absolute quantifier about 50, we are able to translate it in this form. And by now it should be clear that the canonical form, um, uh, it should be clear that given any fuzzy proposition, uh, given the, fuzzy propositions involving absolute quantifier, we are able to translate it in this particular structure. There are Q U's in U such that V U is F. Now, you should notice that we have a fuzzy set F. And what that fuzzy set F describes? It describes a vague concept. In the first case, that vague concept happened to be middle-aged. In the second example, that vague concept happened to be high fluency in the English language. But F describes those vague concepts in general. Recognize what I'm saying. F is a fuzzy set over the set of all variables V can take. Here the variable V is the age variable. It take values in say 0, 100. And therefore F is a fuzzy set over the set of all ages to unit interval. So that is, this fuzzy set F describes the vague concept middle aged in general. If you give me any age, say 82, I can find out to what extent it satisfies the vague concept middle age. Similarly, in the second example, the fuzzy set F models the vague concept high fluency, but it models the concept high fluency in English language in general. If you give me any fluency level, say 8, I can compute to what extent that fluency level satisfies the vague concept of high fluency in English. So this fuzzy set F describes the vague concept in general. But the propositions that we started with are specifically about 15 students in the class or approximately 50 staff members in the college, right? So the propositions that we started with are specifically about the universe U, right? And therefore, by using this insight that the fuzzy set F describes the vague concept in general, but what the proposition but the propositions that we are dealing with specifically talks about the objects in the universe. It talks about staff members or it talks about students in the class. And by using this insight, we can compress this structure even more. So this can be compressed as there are QEs, where Q is the absolute quantifier. In first case, it was approximately 50. In the second case, it was about 50. So the Q part is clear. This fuzzy set E, it's a fuzzy set that describes the vague concept in relation to objects in U. Okay. The fuzzy set F describes the vague concept in general. It describes high fluency in English language in general or middle aged in general. But the proposition specifically talks about the universe, the either staff members in the college or students in the class. And therefore, we define a fuzzy set E over the universe U given in this manner. And this fuzzy set describes the vague concept in relation to the relevant set of objects, namely the set of objects in our universe U. And by using that insight, we are able to compress this syntactic structure. There are q u's in U such that V of U is F. So simply there are QEs. So to make this idea more concrete, consider the first example again. There are approximately 50 staff members in the college, such that their age is in the middle. Such that their age is in the middle. That is this this is basically in this form. There are Q U's in F such that V of U is high, right? And we had a fuzzy set F that captured the vague concept of middle age. But that fuzzy set F captured the concept of middle age in general. But this proposition specifically talks about staff members in the college. So we can define a fuzzy set E like as the middle age staff members in the college. That is, this fuzzy set E, this fuzzy set E is a fuzzy set over the universe given in this manner. That is, given a staff member U, the membership with which it belongs to the vague concept middle age is like this. You first compute the age of that staff member, right? Or in other words, you compute V of U, and then you compute the membership of V of U in the set F. In this particular example, V was the age variable, F was the middle age vague concept. Okay. So from the general concept of middle age, we have jumped to the specific concept of middle-aged staff members in the college. Okay. I hope you are able to recognize why doing this is relevant, right? Because we are interested in the universe U. Okay. And in this intermediate step, we identified the vague concept. We identified the fuzzy set F, and that fuzzy set F modeled the vague concept in the proposition in a general setting. But we are interested in the setting of the universe U. We are interested in the staff members in the college or students in the class, and therefore we can define a fuzzy set E over the universe, capturing the concept middle age or high fluency English speaking students in the class, right? So we can define the fuzzy set E like this. Okay. So for the second example, there are about 15 students in the class such that their fluency in English is high. The fuzzy set F is high fluency. Okay. And it describes the high fluency in English language in general. But this proposition is specifically about students in the class. Therefore, we define a fuzzy set E over this set of U, this set of students in the class, like this. So given a student U, I first find out the fluency of that student. That is, I compute V of U. And then I find out to what extent that fluency level belongs to the fuzzy set high fluency. That is, I compute the membership of V of U in the fuzzy set F. In this particular setting, our variable V is nothing but fluency variable, and our fuzzy set F is nothing but high fluency. So we get this. So the fuzzy set E describes the high fluency English speaking students in the class. Okay. While the fuzzy set F describe all the fuzzy set F describes the high fluency in English language in general. But the fuzzy set E describes the high fluency English speaking vague concept in relation to the universe U, or in other words, it describes high fluency English speaking students in the class. Okay. So I hope by now it is clear that this first canonical form of fuzzy propositions involving involving absolute quantifiers is this. There are QEs, where Q is an absolute quantifier and E is a fuzzy set over the universe describing the vague concept in relation to objects in U. That is, in relation to the relevant set of objects, namely the objects in the universe. And E is defined in this particular manner. Now, the natural question is, how do you compute the truth value of this proposition? Now, if this set E, instead of being a fuzzy set, happened to be a crisp set, like Kashmiri employees in the company or number of tigers in India, then we know how to compute the truth value, right? We simply find out how big that set E is, and having computed that size, I then figure out what is the compatibility of this size to the fuzzy set that represents this vague quantifier, this fuzzy quantifier, namely Q of mod E, right? But here in this case, we don't have a crisp set E, we have a fuzzy set E. And but the philosophy is same, right? If we can find out how big this fuzzy set E is, if we can arrive at some real number describing how big, if we can arrive at a real number, say S, describing how big the fuzzy set E is, then the truth value of this proposition, say P, is the extent to which S belongs to the fuzzy set representing the quantifier Q, right? If we can arrive at a real number that somehow describes the set of this fuzzy, the size of this fuzzy set E, then we can simply figure out to what extent that size belongs to the fuzzy set Q, the fuzzy set that represents the fuzzy quantifier Q, and we will be done. But that we know how to quantify, we know how to describe the size of a fuzzy set if our underlying universe U is finite, and that is nothing but the scalar cardinality. I should write this more clearly to avoid confusion. Scalar cardinality of a fuzzy set essentially tells me how big that fuzzy set E is in terms of like membership, how big, how much membership that fuzzy set E distributes in general to different elements of the universe, right? So this scalar cardinality of a fuzzy set tells me how big a fuzzy set E is. So we know how to come up with a number, a real number, that would give me a sense of size of fuzzy set E. That is, it tells me how big that fuzzy set E is. Now, having computed that size, all that is all that remains is that we is figuring out to what extent that size belongs to the fuzzy set Q, or the fuzzy set that represents the quantifier Q. So in other words, recall mod E captures the size of fuzzy set E, then the truth value of there are Q is nothing but the membership of mod E in Q. So the more appropriate notation is mu Q of mod E, right? Or in other words, basically you can uh, write the formula for mod E to get this, and we know that E is defined in this manner. So you essentially get this. Okay. So take some time and digest the fact that even when we are dealing with fuzzy sets, when we are dealing with fuzzy propositions that involve absolute quantifiers, we can cast them in this form, right? Where Q is an absolute quantifier and E is a fuzzy set that describes the vague concepts in the proposition in relation to the relevant set of objects U. Now, the next question is, how do we compute the truth value of the proposition? So we first find out how big that fuzzy set E is. That is done using mod e. And having obtained that size, we simply find out how compatible it is with the quantifier Q. And that is done by finding out the membership of mod e in the fuzzy set Q. And that is the formula. So for the first example, there are approximately 50 students in the college such that their age in the middle, which is translated, which when translated into this canonical form is essentially this. There are approximately 50. The fuzzy set E here is the middle age staff members in the college, right? And our quantifier Q is approximately 15, right? And this is how the fuzzy set E is, the membership of the fuzzy set E looks like. Then the truth value of this proposition would be Q of mod E, or in other words, Q of this, right? And where the summation, of course, is done over the entire universe. And since our universe consists of staff members in the college, so our summation runs over staff member U. Similarly, for the second example, there are about 15 students in the class such that their fluency in English is high, which when translated into the canonical form, there are QEs, look like this. There are about 50. So our quantified Q is about 50. And the fuzzy set E describes the vague concept, high fluency English speaking students in the class. And the membership of this vague concept E looks like this. And the truth value is given in this manner, Q of mod E. And since membership of E looks like this is what you have. And the summation runs over the entire universe U. And here our universe U consists of students. Therefore, summation runs over student U. Okay. Now let us do a model problem. Um, we have a class of 10 students, and these students have scored these scores in a particular test, and these scores are out of 100. And we are required to find the truth value of these two propositions. The first proposition is approximately 5 students in the class perform decent. So approximately 5 is the quantifier here. It's a absolute quantifier. It's a number type quantifier. And the question says that we have to model that quantifier like this. And we also have a vague concept here, namely decent. And the question says that we have to model that decent, the vague concept decent like this. And similarly, we have to find the truth value of the proposition P2 that involves the quantifier around 3, which is required to be modeled like this. And it involves a vague concept exceptionally well, where well is given like this and exceptionally is a hedge, right? The fuzzy set well is given in this manner, and exceptionally is a hedge which is given to be, which the question says that the question says that the h should be modeled as the cube operation, that is h of a is equals to e cube. Okay, so let's solve this problem. So let us first focus on the first proposition. Approximately 5 students in the class perform decent. Okay, so what is our universe U here? It is the students in the class, set of students in the class. And it is given that there are 10 such students. So there U, our universe of discourse, is the set of all students in the class. Now, what are we interested in? We are interested in the performance of the student in the class. Performance is equivalent to the marks they have scored or the score they have gotten. And therefore, our variable V is the score variable. And it takes values. And the question also says that these scores are out of 100. Therefore, our score variable V take values in 0, 100. In fact, it should be 0, 1, 2, 3, all the way to 100, because generally uh, there is no infinite precision, right? When we talk about scores, the most you get is like a gradation of 0.5. So you have scores like 67.5 or 23.5. It's impossible. It's almost impossible to have a score in a real life setting where you have a score of 27.592 or 5921, right? So an appropriate unit, so the value, so this variable b take values in 0, 1, 2, 3, all the way to 10, or all the way to 100, right? So I should have been more careful, but again, you got the point, right? So even if I assume that my fuzzy set v, even if I assume that my variable v take values in 0, 100, Um, that's not gonna change a lot. The meaning, however, like as I said earlier, the meaning is important, right? So score variable can be assumed to take values in this unit interval, in this interval 0, 100. But to be more meaningful, we should have taken this set of values. But again, I don't want to belabor the point. I think you understood what my point was. Okay. And the way concept decent performance is modeled by fuzzy set f over the set of values that the variable we take, that is, as a fuzzy set over the interval 0, 100. And this fuzzy set f models the vague concept of decent performance. Okay. And the question already says that we need to model this vague concept decent by this fuzzy set, this trapezoidal fuzzy set. And what is our quantifier? It is approximately 5. Okay. So we asked ourselves three questions: what we are talking about, what we are interested in, and what is the fuzzy quantifier. And that helped us identify U, universe of discourse, variable V, fuzzy set F, and the quantifier Q. Okay. Now this fuzzy set F models the vague concept of decent performance in general, but this proposition specifically talks about student in the class. And therefore, we define a fuzzy set E over U that models this vague concept that models this vague concept of decent performance in relation to students in the class. Or in other words, the fuzzy set over U describes or models decent performing student in the class. And how that fuzzy set E is obtained? Given a student U, you simply compute the score of that student, and then you find out to what extent or to what is the membership value of that score in the decent fuzzy set. Okay, so let us now compute this fuzzy set E. So decent is this triangle, this trapezoidal fuzzy number. So what will be the membership function of this decent? So given, so when x is between 50 and 70, we have membership 1. When x is between 40 and 50, we have this as the membership. And when x is between 70 and 80, 80 minus x by 10 is the membership value, and it is 0 everywhere else. Okay. Now 67 lies between 50 and 70, right? So just a minute, I'll make sure that I have my notes with me. Okay. So 67 lies between 50 and 70, therefore its membership is 1. 80, at 80 you have 0, right? Because when x is equals to 80, membership is 80 minus x by 10. So 80 minus 80 by 10, or in other words, 0. 71 is between 70 and 80. Therefore, it's 80 minus 70 by 10, or in other words, it's 9 by 10 or 0.9. And similarly, you can compute the membership values, the other membership values. I'm not going to walk you through the each step, but I hope that is something that you can do on your own, right? 80 minus 76 by 10, and this is 0.4. So we have computed our fuzzy set E, which is the fuzzy set modeling the vague concept of decent performing students in the class. Now we are interested in finding out the truth value of this proposition P1 that tells us approximately 5 students in the class perform decent. So the canonical form of this proposition is there are QEs, where Q is approximately 5 and E is, as I said, it's the fuzzy concept, is the fuzzy set describing the decent performing student in the class. So this is our proposition P1. So what is the truth value of the proposition P1? It's Q of mod E, where Q of course is approximately 5. Now we have find the fuzzy set E. Let us find mod of E. Okay. So mod of E is the sum of all the membership values that the fuzzy set E takes. So 1 plus 0 plus 0.9, so 1.9, 2.9, 3.9, 4.3 plus zero point 0.4, so 4.7. So mod of A is 4.7, right? And therefore, truth value of proposition P1 is Q of mod E, or in other words, Q of 4.7, and Q here is approximately 5, so approximately 5 of 4.7. And the question tells us that the approximately 5 quantifier has to be modeled by this triangular fuzzy number 456. Okay. Now 4.7 lies between 4 and 6. Therefore, the truth value would be x minus 4 divided by 5 minus 4, where x is 4.7. So 4.7 minus 4, or 0.7. So the truth value of proposition P1 is zero point 0.7. Now let us move to the second proposition. Around 3 students in the class performed exceptionally well. Again, the what we are talking about, we are talking about students in the class. Therefore, our universe of discourse U is the set of all 10 students in the class. What we are interested in? We are interested in performance of the students, and performance is equivalent to the score that they have fetched. So our variable V would be the score variable, and it takes values in the interval 0, 100, as is indicated by the question. All right. And what is the wake concept here? It's exceptionally well. Now, the question tells us that the wake concept of well performance is given by this. And exceptionally is a linguistic hedge that has to be modeled like this. This is, again, the question itself mentions this. Then how can we obtain the fuzzy set corresponding to the wake concept exceptionally well? We simply apply it to the we apply the hedge h to the membership function of the fuzzy set well, and that would give us the membership function of well cubed. So in other words, the fuzzy set f that models the wake concept involved in proposition P2, which is the wake concept exceptionally well, the membership function of that fuzzy set f is given in this manner. So I hope that is clear. And the quantifier here is around 3. Now, as I have mentioned multiple times by now, this fuzzy set f models the wake concept of exceptionally well performance in general, but the proposition P2 is specifically about student in the class. And therefore, we define a fuzzy set E that models this wake concept of exceptionally well performance in relation to the student in the class, or in relation to the universe U. And that is done in this manner. That is, given a student U, its membership to this wake concept of exceptionally well performing student in the class is obtained by first computing the score and then finding out to what extent that score belongs to the fuzzy set F, which is the fuzzy set describing exceptionally well performance in general. Okay. So let us compute that. Again, well looks like this, right? This is the fuzzy set for well, and this is the membership function of the fuzzy set E. So all we have to do is essentially cube this mu well score U. Now mu well score U is something that we have already computed, right? Notice that this is, oh sorry, this was decent, right? Oh sorry. Which means that we cannot escape work here. We have to do everything from scratch. I thought that in the first proposition P1, instead of decent, we had will. Anyways, so well is given by this. So let us quickly write the membership function of well. It's 1 if x is between 90 and 100. It's x minus 75 divided by 90 minus 75, which is, I think, 50, if I'm not wrong. If x is between right? Okay. So this is the fuzzy set well. So it's actually a trapezoidal, degenerate trapezoidal, right? Because the last two parameters are same. So it looks something like this. From 75 to 90, you have a linear increase, and then you have 100. Uh, anyways, So let us quickly compute this fuzzy set E. So 67 is and by the way, it is zero everywhere. So 67 is less than 75. Therefore, it is zero cube, or in other words, zero. At T lies between 75 and 90. So therefore, at T minus 75 divided by 50 cube, or in other words, this is 1 by 5 by 15. 5 by 15 is 1 by 3. 1 by 3 cubed is 1 by 27. 71 is smaller than 75. So this is 0. This again is 0. This again is 0. These are essentially 0 cubes. So we get 0 only. 90 is greater than or equal to 90. So you get 1 cube here, which is 1. This again is 1 cube. So this is 1. This is 0 cube. So 0, 0 cube, 0. 76 lies between 75 and 90. So 76 minus 75 divided by 15 cube, or in other words, 1 by 15 cube. So what is 15 cube? It's 1 by 3375. So this is our fuzzy set E. Let us quickly compute the membership value, the scalar cardinality of E. It's nothing but the sum of all the membership values of fuzzy set E. So the only non-zero membership values is 1 by 27, 1 plus 1, and plus 1 by 3375. So this turns out to be 764 divided by 375, or in other words, it's like 2.03, right? Um, okay, around 2.03. Now around 3, so the truth value of proposition P2 would be Q of mod E, or in other words, Q of 2.03. And or it's okay to just use the fraction only. Why do the simplification? And Q is around 3 here. So membership of 764 divided by 375 in around 3. Now 764 by 375 is 2.03. So it lies between 2 and 3. And therefore, the membership of 764 divided by 375 in this fuzzy set would be given in this manner, right? And this turns out to be 3 by 2 is 1 only. So denominator is 1. And so 375 times 2. So it's 600, 750. 764 minus 750 is 40. And this turns out to be 0.037. Okay. So this is the truth value of proposition 2. So I hope you got a sense of how to compute the truth value of fuzzy propositions involving absolute quantifiers. Now, as I said earlier, that fuzzy propositions involving absolute quantifiers are of two types. The one that we discussed, whose canonical form was there are QEs, is of the first form. Let us now discuss the second form. So a few examples of proposition, second form of fuzzy propositions involving absolute quantifiers are these two. So there are about 10 students in the class whose fluency in English is high and who are young. The number of tall and underweight patients in the hospital is close to 15. So again, we have an absolute quantifier, about 10, close to 85. And instead of a single vague concept, we have two vague concepts. So here we have fluency, high fluency in English language, and young. Similarly, in the second example, we have tall and underweight patients. So the first form differs, the first form is different from second form only in that the first form has one vague concept and the second form has more than one vague concept. In this case, we have two vague concepts, right? So let us analyze this um, analyze these examples and try to extract a canonical form. Okay. Suppose I consider this proposition. There are about 10 students in the class whose fluency in English is high and who are young. What we are talking about, students in the class. So what will be our universe? It will be the set of all students in the class. What we are interested in? We are interested in fluency in English language as well as the age, right? So we define two variables. V1 would be the fluency variable. It take values V1 U for each student U. And then we define a variable V2, which would be the age variable that assumes the value V2 U for each student. So the fluency variable can take values in 1, 2. This is something that I already explained. And the age can take values in 0, 100, right? And we have two vague concepts, high fluency in English language and young. So high can be modeled. Again, high fluency in English language is a vague concept, and it is modeled by fuzzy set F1. And this is a fuzzy set over the set of values of variable V1. Similarly, young is a vague concept, and it is modeled by fuzzy set F2, which is a fuzzy set over the set of values of variable V2. Okay. And the quantifier, of course, is about 10. So Q is an absolute quantifier corresponding to about 10. So I hope you're able to recognize that in this second form, we have a quantifier Q, we have a universe of discourse U. The only difference is instead of one V and one F, we have two V and two F. That is, we have more than one vague concept. Similarly, okay. Now we can restate this proposition in a manner where this universe of discourse U, variables V1, V2, fuzzy sets F1, F2, and Q becomes evident, namely in this manner. So there are about 10 students in the class. So there are Q U's in U. Q here is absolute 10, and U in use is basically students in the class, such that their fluency in English is high, such that V1 U is F1, and they are young, or in other words, their V, V2 U is F. Now, again, I could have rephrased this proposition in a manner that would have exactly fit this structure, that there are 10, about 10 students in the class such that such that the fluency of the student in English is high and fluency of student in such that age of student is young, right? But that sounds a bit awkward, right? And that is why I state this in this manner. So instead of using the student here, I'm using they are young, but this is like semantically meaningful, right? But the underlying structure is this only. There are Q U's in U such that V1 U is F1 and V2 U is F2. Okay. For the second proposition, let's do the same analysis. We are talking about patients in the hospital. So our universe U would be the set of all patients in the hospital. What we are interested in? We are interested in the height of patients, and we are interested in weight of patients, right? So we define two variables, V1 and V2. V1 is the height variable, and it take values V1 U for each patient U. And similarly, I define V2 to be the weight variable that assumes value V2 U for each patient U. So V1 can take values from 50 to 30, or basically 0 to 250 centimeter. And V2 can take values from 0 to 300 kgs, right? Of course, one can identify an appropriate universe for V1 and V2. Now, tall, what are the vague concepts? Tall and underweight. And this vague concept tall is modeled by a fuzzy set F1 over the set of values of variable V1. And the second vague concept underweight is modeled as a fuzzy set over the set of values of variable V2. Okay. So I hope this was clear. What we have done here is what we had done earlier also. Okay. So I hope that that was clear. And what is the quantifier here? It is close to 85. So Q is the absolute quantifier corresponding to close to 85. Now, again, I can rephrase this proposition in a manner where these parameters become evident, namely like this. There are close to 85 patients in the hospital such that they are tall, V1U is F1, and they are underweight such that V2U is F2. Close to 85, our quantifier Q. Patients in the hospital, U's in set U. They are tall. V1 is V1U is F1. They are underweight. V2U is F2. So I hope you are able to recognize by now that the structure of the structure of fuzzy propositions involving an absolute quantifier and having more than and having two vague concepts is this. Now again we make the same observation. F1 and F2 describe the vague concepts in general, but the proposition this proposition is specifically about patients in the hospital. Similarly, this proposition was specifically about student in the class. And therefore, we can compress this structure into this. There are Q E1 and E2s, where E1 and E2 describes the vague concepts in relation to the relevant set of objects, or in other words, over the universe U. And this is how E1 and E2 are defined. Again, what we are doing is same as what we have done earlier. The only difference is we have two vague concepts here, and therefore we have two fuzzy sets, E1 and E2. So let us take what are E1 and E2 in this particular context. E1 would be the high fluency English speaking students in the class. So this is this the proposition. This particular is when we express the first example in this particular structure, this is what we get. There are about 10 students in the class so that their fluency in English is high and they are young. And then we can compress it even further by defining fuzzy sets E1 and E2. And this E1 and E2 describes high fluency in English language in relation to students in the class. E2 describes the young being young in relation to students in the class. And they are defined in this particular manner. And therefore, we are able to compress this even further in this manner. There are Q, E, and E1. In other words, there are about 10 high fluency young students in the class. There are about 10 high fluency English speaking students and in the class and young students in the class. Again, I don't want to state this proposition in exactly this manner. That is why I have shifted in the class to the extreme right. In other words, there are about 10 high fluency English speaking and young students in the class. Okay. And this is the E1 and E2. Similarly, for the second example, this is how we rephrased our second example to get this particular structure. There are Q U's in U such that V1U is F1 and V2U is F2. All right. Now, again, the set F1 and F2 in this particular set described the vague concept of tall and underweight in general, but the proposition specifically talked about patients in the hospital. And therefore, we define E1 and E2 that describes tall patients in the hospital, underweight patients in the hospital. And the membership of these fuzzy sets E1 and E2 are defined in this manner. Okay. So long story short, the second form of fuzzy propositions involving absolute quantifiers is this. The canonical form is this. There are Q, E1, and E2s. This is in contrast with first form where we just had there are Q E1s. Okay. So in the second form, you have two vague concepts and therefore you have E1 and E2 and therefore the canonical form is there are Q, E1, and E2s. Q is absolute quantifier and E1 and E2 are fuzzy sets over the universe expressing the vague concepts in relation to U, right? In relation to what is relevant and not like vague concepts in general. Now the question is how to compute the truth value of this proposition. Now, if E1 and E2 were to be crisp sets and not, say, fuzzy sets, then things would have been easier. Why? Suppose I say there are around 80 employees in the company that are from Kashmir, and who have studied in Delhi. Then even here would be set of all employees that are from Kashmir, and E2 would be set of all employees that who have studied in Delhi. So the subset of universe that interests us is the crisp set E1 intersection E2, right? That would give us the collection of all employees in in the company who are both from Kashmir and have studied in Delhi. And we can then compute its size E1 intersection E2. And having computed its size, I can then figure out how compatible that size is with the fuzzy quantified Q. And that can be done by finding out the membership of mod of E1 intersection E2 in the fuzzy set corresponding to quantified Q. But here, instead of having crisp sets, we had fuzzy sets. But again, we can get a size, we can get a sense of size for fuzzy sets as well. All we have to do is take the scalar cardinality. So what we do is we take the scalar cardinality of E1 intersection E2. And then we find out what is the membership of that scalar cardinality in the fuzzy set corresponding to quantifier Q. And I'm using this notation as I have said earlier. So the truth value of there are Q E1 and E2s is Q of mod E1 intersection E2. Now, if you substitute the formula for mod of E1 intersection E2, this is what you get. And therefore, for the first example, the truth value of there are about 10 high fluency English speaking and young students in the class would be you first you first define the fuzzy set C1 and E2 that respectively captures high fluency English speaking student in the class and young student in the class. You take their intersection and compute the scalar cardinality, and then you compute the whatever number you got, you compute the membership of that number in the fuzzy set corresponding to quantified Q. Similarly, the truth value of proposition there are close to 85 tall and underweight patients in the hospital like this. You define the appropriate E1, E2, E1, E2, and then you take the intersection, you compute the scalar cardinality, and then you compute the membership of E1 intersection E2 ka scalar cardinality in Q. Q here is the fuzzy set corresponding to the quantified close to 85. Okay, and this, of course, if you expand E1 intersection E2's scalar cardinality, this is what you get. Okay, so let us quickly do a problem. Um, Again, we have the same setting as before, but in addition, okay, we have 10 students again, and their fluency level and age are given. Fluency level varies from 1 to 10 and age varies from 0 to 100. And these are the values of those two parameters for different students. And we are required to find the truth value of the following proposition. There are about 4 students in the class whose fluency in English is high and who are young. Right? So basically the first example that we considered. And we have said that model the vague concept of high fluency, basically high as x by 10. So if fluency of someone is 9, fluency level of someone is 9, then that fluency level belongs to the fuzzy set of high fluency to 0.9 degrees. So you just divide by 10. And the vague concept of young is specified to be modeled by fuzzy set 0, 0, 15, 30. And the quantifier about 4 is specified to be modeled as 246, the triangular number 246. So let us look at the proposition P. There are about 4 students in the class whose fluency in English is high and who are young. What is our universe? What is U here? What we are talking about? We are talking about student in the class. So U becomes students in the class, set of all student in the class. And we are given 10 such students. So the set of 10 students in the class. What are we interested in? We are interested in fluency in English language and age. So we define two variables, V1 and V2. V1 is the fluency variable, V2 is the age variable. And what are the vague concepts involved? High fluency in English and young. So F1 and F2, F1 would be a fuzzy set over the set of values of variable V1, modeling the vague concept of high fluency in English. And F2 would be a fuzzy set over the set of values of variable V2, modeling the vague concept of young. But and what is the quantifier Q? It is about 4. But F1 and F2 models the vague concept of high fluency in English and young in general. But this proposition P is specifically about student in the class. And therefore, we define fuzzy sets E1 and E2 to model the vague concept of high fluency English speaking students in the class, right? So we are moving from the general concept of high fluency English speaking, high fluency in English language to high fluency English language in the context of our universe, namely in the context of the class. Similarly, we define E2 that models the vague concept of young student in the class. So even U would be given by, so F1 in this case is high fluency and the variable V1 is the fluency level. F2 here is young, the vague concept young, and the variable 2U is the age variable, right? So in other words, this is our fuzzy set E1 and E2. And what is the quantifier? It's about 4. So we are interested in finding the truth value of proposition P. We have already seen that the truth value of this proposition is nothing but scalar cardinality, or the membership of scalar cardinality of E1 intersection E2 in the fuzzy set that corresponding to the quantified Q. So we first um, compute E1 and E2, and then we'll compute E1 intersection E2. Okay. So let us start by computing the set E2. So let's start first by E2. Now, E2 is this, right? And the young fuzzy set is supposed to be modeled like this. And we make the observation that all the ages that are given to us are greater than 15. So we are interested in this part only, right? And for age X between 15 and 30, the membership of that age in the in the fuzzy set young is 30 minus X by 50. So this will be 30 minus 17 by 15, or in other words, um, I'll quickly grab my notes. So 30 minus 17 by 15, so 13 by 15, 30 minus 24, so 6 by 15, and similarly 10 by 15, 5 by 15, 30 minus 21 is 9, so 9 by 15, 1 by 15, 5 by 15, 7 by 15, 11 by 15, and 10 by 15. Now let us compute E1. So E1 is fairly straightforward to compute. You just give me, you first find out the fluency value, and then you compute its membership in the fuzzy set high. And the fuzzy set high has a fairly straightforward expression. So this is nothing but 1 by 10 fluency of U. So this would be 0.5, zero point 0.8, and so on. But since we also have to compute E1 intersection E2, which is nothing but minimum of mu E1 U, comma mu E2 U, and the membership values in the fuzzy set E2 all have a denominator of 15. So in order to facilitate easy comparison, what we will do is write the write it like this. So fluency of U, I want to make sure that it has a denominator of 15. So in other words, 3 by 2 fluency of U divided by 10. Okay. Sorry, by 50. Right. 3 by 2 of 5 is um, 7.5. And this is 12, um, 13.5, 10.5, 9, 15, uh, right? So in other words, this is the value of so right. So this is and then you can take the minimum. So if you take the minimum, what will you get? Minimum of 10.5 and 5 is 5. Right? In other words, this is the set even E2 and even intersection E2. Now let us compute the scalar cardinality of even intersection E2. So 7.5 plus 13, 13, 23, 28, 37, 38, 38, 43, 47, 50, 56, and then 57. So 57 by 50, right? And we have to find the truth value of proposition. So that's nothing but Q of E1 intersection E2. Or in other words, Q of 57 by 50. And what is Q here? It is about 4. Therefore, we get this, right? Now, about 4 is given to be modeled by this triangular fuzzy number. So 57 by 50 lies between where? So 15 times 3 is 45 and 15 times 4 is 60. It lies somewhere here, right? That is, it lies between 2 and 4. And therefore, its membership would be x minus 2 divided by 4 minus 2 at 57 by 50. Or in other words, 1 by 2, 57 by 50 minus 2, 1 by 2. So 57 minus 30 by 50. In other words, 27 by 30 or 9 by 10 or zero point 0.9. So this is the truth value of proposition P. Okay. So we are done with our discussion on fuzzy quantifiers involving fuzzy propositions involving absolute quantifiers. They are of two forms. First form, may you only have one wake concept. In second form, you have two wake concepts. And we have seen what's their canonical form and how to compute their truth values. Now let us discuss quantified fuzzy propositions involving quantified fuzzy propositions involving relative quantifiers. These again are of two basic forms. We start by discussing the first form. An example of such a proposition is a few students in the class are tall. So let us analyze this. A few students in the class are tall. So what are we talking about? We are talking about students in the class. So Q is the set of all students in the class. U is the set of all students in the class. What are we interested in? We are interested in the concept tall. So our variable V would be the height variable that for each student U takes the value VU, giving the height of the student. And tall is the vague concept. Therefore, F would be a fuzzy set over the set of values that this variable V can take, this age variable V can take, maybe from 0 to 100. So F is a fuzzy set over the set of values of variable V that models the vague concept tall. Okay. And our quantifier Q is few here. Okay. So we have identified U, variable V, fuzzy set F, and quantifier Q. Now we can restate this proposition in a manner where these four parameters become clear, namely like this. So among students in the class, or in other words, among U's in set U here is the set of student in the class. So U's in set U is nothing but among the students in the class. So among student in the class, there are Q U's in U's. That is, there are a few students such that they are tall, or in other words, such that V of U is F. Okay, take a moment to digest this. Among U's in set U, there are Q U's in set U such that V of U is F. Again, I could restate this proposition in a manner that exactly fits this. That is, among students in the class, there are a few students in the class such that they are tall. But repeating student in the class here as well would have made the sentence a bit awkward, and therefore I am skipping that to have a semantically meaningful sentence. But you can do that, right? But that would have made the sentence a bit awkward or verbose. But the underlying structure is this, and that is what you should recognize. Among U's in set U, there are Q U's in U such that V U is F, right? So this is our syntactic structure. We again make the observation that the fuzzy set F talks about the vague concept of tall in general, but this proposition is specifically about student in the class. So that we can compress this structure to get this. Among U's in U, there are QEs, where E is the fuzzy set describing the vague concept, in this case, vague concept of tall, in relation to the students in the class. Or in other words, E would, in the context of this example, would describe the tall students in the class. And this is how the membership function of E is given. Okay, and Q is of course the relative quantifier. So for this particular example, our quantifier Q, the relative quantifier Q is again few. And what is fuzzy set E? It is the fuzzy set describing tall student in the class, right? And this is how the membership function of E is given, right? So this is the first form of fuzzy propositions involving relative quantifiers. Now let us look at how we can compute the truth value of such propositions. Now again, if instead of having a fuzzy set E, we had a crisp set E, then the truth value of this proposition would essentially be obtained by computing this ratio and then finding out to what extent it is compatible with the quantified Q, which is nothing but the membership of this ratio in the fuzzy set corresponding to quantified U, right? So for example, if um, we had a sentence that approximately 2/5 of world's population have O plus blood group, then we will find the proportion of people in the world who have O plus blood group. In that case, our universe U would be the set of all people in the world, as we have already discussed, and E would be the set of all people who happen to have O plus blood group. And therefore, the ratio mod E by mod U would tell you the proportion of people in the world that have O plus blood group. And then you will find out what is the compatibility of this ratio, this proportion, with the quantifier approximately 2/5. And that is essentially obtained by finding out the membership of that proportion in that fuzzy set representing the quantifier approximately 2/5. But here, instead of crisp set E, we have a fuzzy set E. But again, we don't have to worry about that. We can still get a sense of proportion E by U by taking a cardinality, the scalar cardinality of fuzzy set E, and dividing it by the size of the universe U. Now this would give me a sense of proportion of objects in the universe that belong to this vague concept. Okay, it will give you a sense of that. Again, I'm using the word belong, but belong in the fuzzy setting is not a crisp property, right? Members belong to fuzzy set to different degrees. That's why I'm saying that this ratio mod E by mod U, where mod E is the scalar cardinality of fuzzy set E, would give you a sense of what is the proportion of objects belonging to the fuzzy set E, right? A sense of that. And once you have obtained that ratio, that proportion, you can simply find out how compatible it is with the quantified Q. And that can be done by computing the membership of mod E by mod Q in the fuzzy set corresponding to quantified Q. Or in other words, the truth value of among U's in set U there are QEs. This is what you do. Okay. And if you expand the expression, if you write down the formula for mod E, this is what you get. And you can then substitute in the formula for membership function of E to get this. So I hope you got a sense of how to compute truth value of fuzzy quantified fuzzy propositions that have this as the canonical form. Okay. So in the previous setting, in the previous example, among the students in a few students in the class are tall, which is translated to among the students in the class there are a few are tall. That is in this particular canonical form. Our truth value would be given as Q of mod E divided by mod U, where Q is the fuzzy set corresponding to the quantifier few, and mod E is the scalar cardinality of the fuzzy set E, and E stands for the fuzzy set describing tall student in the class, and the membership of E is given like this. Okay. Now, let us now look at the second form of fuzzy propositions involving relative quantifiers. So an example of such proposition is this. Almost all old employees in the company are overweight. Okay. So how is this proposition different from propositions of the first form? In the first form of quantified propositions involving relative quantifiers, we have only one vague concept, and that vague concept in this case was tall. However, in the second form, we have two vague concepts. Among almost all old employees in the company are overweight. Old. Again, old is a vague concept. It is not meaningful to say that someone is exactly old or someone is not old. Everyone is old to different extent, right? So almost all old employees in the company are overweight involves a relative quantifier almost all and two vague concepts, namely old and overweight. Now let us analyze this proposition. What we are talking about? We are talking about employees in the company. So our universe of discourse U would be the set of all employees in the company. I keep committing that mistake. Set of all employees in the company. And what we are interested in? We are interested in age and weight of the employees. So we define two variables V1 and V2. V1 is the age variable, which for each employee U tells me their age. And this take values in 0, 100. Similarly, the variable V2 is the weight variable, which for each employee U tells me their weight. So it can be from 0 to 300 kg, right? And old is a vague concept, right? And it is modeled by a fuzzy set F1 over the set of values of variable V1. And this models the vague concept old. Similarly, we have a vague concept overweight, and that is modeled by a fuzzy set F2, which is a fuzzy set over the set of values of variable V2, right? And we have a quantifier almost all. And this is, of course, a relative quantifier. And this is what Q stands for. Okay. So we have identified our universe of discourse by answering the question what we are talking about. And then we asked ourselves the question what we're interested in. And that led us to identify the variables V1 and V2 and fuzzy sets F1 and F2. And finally, we asked ourselves what is the quantifier, and we identified Q by answering that question. Now we can restate this proposition in a manner where these parameters become much more apparent, namely like this. Among employees in the company, or in other words, among U's in set U, such that V1U is F1, or in other words, among employees in the company that are old, or among employees in the company such that they are old, there are Q U's in U such that V2U is F2. That is, there are almost all is our quantifier who are overweight. V2U is F2. Now, again, I could have stated this proposition in a manner that would have exactly fit this form. Among employees in the company such that employee is old, there are almost all employees such that employee is overweight. But again, that sounds very awkward and verbose. And therefore, I use this restatement instead. But the syntactic structure is this only. Among employees in the company that are old, there are almost all who are overweight. Okay. So this is the syntactic structure. And we realize that we again make the same observation that F1 and F2 describe the vague concepts in general, but what we are interested in is that vague concepts in relation to the universe of discourse, namely employees of the company. And therefore, we define two fuzzy sets E1 and E2, and they describe the vague concepts in relation to the relevant set of objects. And these are the membership functions of E1 and E2. And having defined E1 and E2, you can compress the syntactic structure into this form. Among U's in U, among U's in set U, Q E1s are E2s. Okay, take some time and recognize this. Among U's in U such that V1 U is F1, there are Q U's such that V2 U is F2, right? So among U's and U stays such that V1 U is F1, there are Q V2 such that V2 U is F. This translates to Q E1s are E2s. So maybe taking an actual example would help you understand why this compression is legit. Almost all old employees in the company are overweight. We translated it into this syntactic structure. Among employees in the company that are old, there are almost all who are overweight. So first of all, we are talking about almost among employees in the company, right? So we're talking about employees in the company. Then we are focusing on old employees in the company. And in that old employees in the company, we are talking about there are almost all who are overweight. So Q evens, right? Q evens. Among the employees in the company that are old, I am doing a quantification of almost all in relation to being overweight. So Q evens. Q evens are E2s. I hope you are able to see that. Okay. So in other words, for when we express our proposition in this canonical form, we get among employees in the company, almost all are overweight, right? So among employees in the company, Q almost all. E1 is the set of all old employees in the company. A2 is the set of all overweight employees in the company, right? So given a proposition, we identified U, V1, V2, F1, F2, and Q. And that led us to this long syntactic form. And then making the observation that F1 and F2 describe the vague concepts in general, while what we need are the vague concepts in relation to universe U. We define universe E1 and E2. And from this syntactic structure, we arrive at this form, which we consider to be the canonical form. And in this particular setting, this is our quantifier Q would be almost all, right? Our fuzzy set E1 would be the fuzzy set describing old employee in the company whose membership is given like this. And E2 would be the fuzzy set describing overweight employee in the company whose membership is given like this. So I hope you are able to see uh, uh, why this is the canonical form, right? Why we take this to be the canonical form. Okay. Now the question is, given given a quantified, given the second form of fuzzy proposition with relative quantifier, how do I compute its truth value? Now notice that what exactly this proposition is implying. It is talking about employees in the company, right? So our universe of discourse is the company, employees in the company. And then it is talking about old employees and overweight employees. So we have a collection of companies, collection of employees in the company that are old. And this collection is a vague, it's a fuzzy set, right? It's given by a fuzzy set because old is a vague concept. So this collection of old employees in the company, it's a fuzzy set. And similarly, we have overweight employees. So the collection of overweight employees in the company is again given by a fuzzy set because old is a vague concept. And then this part tells me that almost all old employees are overweight, right? So it is telling me, it is implying a subset relationship. But this subset relationship is being implied for fuzzy sets old employee and fuzzy set overweight employee, right? If instead of almost all, we simply had suppose we had, maybe it is useful to first take an example where all the concepts are crisp among employees in the company that are from Kashmir. Almost all have a degree in math, right? So among employees in the company that are from Kashmir, almost all have a degree in math. So here even would be the employees in the company who are from Kashmir, or in other words, even is the collection of Kashmiri employees in the company. And E2 would be the set of employees in the company who have a degree in math. And then we have this statement, this quantified proposition implying that almost all Kashmiri employees have a degree in math. So how do we make a sense of a statement like this? We look at even the set of all the Kashmiri employees in the company, and then we find out to what extent it is included in the set of all employees who have a math degree. So even could look like this, and E2 can look like this. So we find out to what extent even is included in E2. And that can be computed easily, right? So you just do this. You compute the degree of subsethood of even in E2. And this would tell you to what extent the set of Kashmiri employees in the company is included in the set of employees who have a math degree. And then you find out to what extent this degree of inclusion is compatible with the quantifier almost all. That is, you find out the membership of this degree of inclusion, this degree of subsethood of even in E2 in the fuzzy set representing the quantifier almost all. Okay. So for this particular proposition, you consider the collection of all old employees in the company, and then you consider the collection of all overweight employees in the company. You find out to what extent this collection of old employees is included in the collection of all overweight employees. In other words, you find the degree of subsethood of even in E2, that is, you find S of even in E2, and this is given by even intersection E2 divided by even. And having obtained this degree of subsethood, you find out to what extent it is compatible with the quantifier almost all. Or in other words, to what extent it belongs to the fuzzy set representing the quantifier almost all. And therefore, the truth value of among U's in set U such that uh, Q evens are E2s is given in this manner. Okay. Just a minute. Okay. So we have seen the two forms of fuzzy propositions involving relative quantifiers. In first form, we had one vague concept. In second form, we had two vague concepts. And we have seen how to compute the truth value of both those two forms. Okay. So for this particular example, among employees in the company, almost all old employees are overweight. In this particular context, E1 was this, E2 was this. Therefore, truth value of this proposition would be Q of S1 of E1 comma E2. So this quantity S of E1 comma E2 tells me to what extent the collection of all employees in the company is included in the collection of overweight employees in the company. And then this whole thing Q of S1 of E1 comma E2 tells me to what extent this degree of subsethood is compatible with the fuzzy quantifier almost all. Okay. And you can write the formula of S of E1 comma E2 and then you can expand it to get this. Okay. So in this particular setting, E1 was given like this, E2 was given like this. So this is the formula you end up getting for the truth value of this proposition. Okay. Let us do a problem. We have a class of 10 students again with fluency level from 1 to 10 and age 0 to 100. And we are asked to compute the truth value of these two propositions. And we are given that quantifiers approximately half needs to be modeled like this, almost half should be modeled like this. High and young are given by these fuzzy sets. So let us start with the first proposition. Approximately half of the students in the class are young, right? So what would be the canonical form of this proposition? Among U's in U, there are QEs. What is U? It's the answer to the question what we are talking about. And we are talking about students in the class. So this is set of all 10 students in the class. What is Q? Q here is approximately half. Right? And what is E? It is the set of young students in the class. So in the intermediate step where you define the variable B and F, here the variable V would be age variable and fuzzy set F would be young fuzzy set. And it would be a fuzzy set over the set of values of age variable. But that fuzzy set F would describe the vague concept of young in general. But we are interested in vague concept in relation to students in the class. And that is captured by fuzzy set E. Okay. So Q would be approximately half, F would be fuzzy set describing young students in the class. And if we restate P1 in the canonical form, this is what we get. Among students in the class, there are approximately half who are young. Okay. And this is basically how the membership function of E looks like. Now let us compute the this fuzzy set E. Now, this is something that we had already done in the last model question, right? So I'm not doing it again. I have just copied the values from the previous question. And add, let us compute the scalar. Now, the truth value of this proposition P1 is nothing but mod of E1 divided by, sorry, mod of E divided by mod of U, right? So we start by computing mod of E. So 13 plus 6 is 19, 29, 34, 43, 44, 49, 56, 67, 77. So 77 by 50, right? And we have to, so the truth value is this Q of mod E by mod U. So 77 by 50 divided by 10 because our universe U has 10 students. So 10. And our quantified Q is approximately half, which is modeled by this fuzzy set. So therefore, truth value is the membership of 77 by 15 divided by 10 in approximately half. So this is nothing but approximately half So 77 by 15 is what? Just a moment. So 15 times 5 is 75, right? And 15 times 6 is 105, right? Sorry, 90. Okay. And 77 lies between this. Therefore, this 75 by 15 lies between 5 by 10 and 7 by 10. Okay. And therefore, this is 7 by 10 minus x divided by 7 by 10 minus 5 by 10 at x equals to 75 by 15 divided by 10. So this is nothing but 7 minus 77 by 15 divided by 2, 1 by 2. So 7 times 15 is 105 minus 77 by 15. And this is 1 by 2. And what is this particular value? This is 105 minus 77. So 25, 27, right? By, so 30. I hope I'm not committing a mistake here. Okay, so this is perfect. Okay. So the truth value of this proposition would be 0.9. All right. Moving on. Almost all the young students in the class have high fluency in English. So again, we restate this in the canonical form. Among U's in U, Q evens are E2. What is Q? Q is almost all. And what is even? Young students in the class. And what is E2? High fluency English speaking students in the class. How we arrive at even in E2 is not something I'm going to repeat again. I have repeated it enough times. So I hope you have gotten a knack for it. This is the quantifier. This is the fuzzy set even in E2. Now, this is the second form of fuzzy proposition with relative quantifiers. So what will be truth value of this proposition? It is Q of S of E1, comma E2. Okay. Now let us quickly compute E1 in E2. Now E1 is basically the set of young students in the class, and therefore this is how the membership function of E1 looks like. And E2 is the set of high fluency English speaking students in the class, and therefore this is the membership function of E2. And we have already computed E1 in E2 in the previous question. However, in the previous question, this was fuzzy set E2 and this was fuzzy set E1. But nonetheless, we had computed these membership functions before. So I quickly copied the values from E1 and E2 from the previous problem. And E1 intersection E2 turned out to be this, right? So let us now quickly compute the scalar cardinality of E1 intersection E2 and E1, because S of E1 comma E2 is nothing but E1 intersection E2 divided by E1, right? So 7 plus 6 is 13, 13 plus 10 is 23, 28, 37, 38, 43, 47, 50, 56, 57. 57 by 15. And this we had already computed to be 17 by 15. Okay, so this is 57 by 15 and 77 by 15. Right? Okay. And therefore, the truth value of this proposition would be Q of this. And Q happens to be almost all in this case. So almost all of 57 by 15 divided by 77 by 15, or in other words, 57 by 77. And almost all is given in this particular manner, right? So I have to make a comparison with this value. So let us write 57 by 77 as this, right? And 57 uh, this value, the numerator value, turns out to be 7.142. So in other words, 57 by 77 is between this and this, 6 by 10 and 9 by 10. And therefore, this value, almost all, membership of 57 by 77 in the fuzzy set almost all, is given by this. And when you compute this value, you end up getting 0.46. So truth value of proposition P2 is 0.46. Okay. So we have talked about fuzzy quantifiers. We have talked about crisp propositions with fuzzy quantifiers and fuzzy propositions with fuzzy quantifiers. And with fuzzy propositions with fuzzy quantifiers, we developed two canonical forms for absolutely quantified fuzzy propositions and two canonical forms for relatively quantified fuzzy propositions. And in both the cases, the first form differs from the second form in the sense that first form involves one wake concept and the second form involves two wake concepts, right? And we identified these canonical forms by asking ourselves three questions. What are we talking about? What are we interested in? What is the fuzzy quantifier? Okay. And once you answer these questions, this tuple becomes evident. And you can then restate your fuzzy proposition in a manner where these Q, V, F, and Q, U, V, F, and Q become apparent. And this restatement of fuzzy proposition does not change the meaning at all. And I hope you have recognized it. Although I have not stated that in so many words, but all the restatements of propositions that we had done did not change the meaning of those propositions. It's not that we identified an extra piece of information while doing the restatement. We were just restating fuzzy proposition in a different manner. So, anyways, so we identified this tuple U, V, F, and Q, and we restated our fuzzy proposition, and then we did a level of compression to get these four canonical forms. So this involves absolute. So these two has to do with absolute quantifier, and these two has to do with relative quantifiers, right? And once we compressed these restatements, we ended up getting the canonical forms. So there are QEs, there are QE1 and E2s. These are again for absolute quantifiers, and these are for relative quantifiers. And once a proposition is expressed in a canonical form, computation, its truth value computation becomes fairly straightforward, right? So for this particular form, we have this truth value. For this particular form, we have this truth value. For this particular form, we have this truth value. And for this particular form, we have this truth value. Now, if you notice this table a bit carefully, you would recognize something very interesting. Suppose I write a proposition W is Q, where Q is a quantifier. Now, a quantifier is a fuzzy number, either over the real line or over the unit interval. But at the end of the day, it's a fuzzy set only. So Q is a fuzzy set. And W is some variable that take values in some universe. Okay. So this is variable W. And this variable W take values in some universe, set V, set W. Now, this proposition is an unconditional and unqualified proposition, the most simple kind of proposition one can hope for. And how do we compute the truth value of such a proposition? If we know that the variable V takes the value W, then the truth value of this proposition, say P dash, would be Q of W. So in this particular case, the value that the variable W took was mod of E. In this particular case, the value that variable W took was scalar cardinality of E1 intersection E2 or mod of E1 intersection E2. In this particular case, E1 took the value mod E divided by mod U. In this particular case, it was mod E1 intersection E2 divided by mod E1. So all these four canonical forms that we uh, uh, so patiently derived only differ syntactically. As far as their truth value computation is concerned, they behave similarly. They behave like this proposition W is Q, where the variable W take different values for different canonical forms, right? So in this particular case, so all these four canonical forms that syntactically are different, computationally they behave like this proposition W is Q. For first case, W take values in as the scalar cardinality of E. In second case, W take values as again a scalar cardinality of a fuzzy set, but this fuzzy set happens to be E1 intersection E2. In third and fourth case, it take values as this. So in the last case, it is the degree of subsethood of E1 in E2, right? And in the third case, it is mod E by mod U. And this is nothing but degree of subsethood of E in U. I hope you are able to see that. Degree of subsethood of E in universe U is nothing but mod E by mod U. Convince yourself of that. So in the first two cases, the variable W take values as scalar cardinalities of fuzzy sets. And in the second two cases, in the last two cases, the variable W take degree of subsethood as values. So all these four canonical forms differ syntactically. And as far as truth value computation is concerned, they behave similarly. Namely, in this particular manner, W is Q, where the variable W either takes scalar cardinality of fuzzy sets as values or as degree of subsethood of some fuzzy set in some other fuzzy set as value. Okay, so that concludes our discussion on the truth value computation of fuzzy propositions and crisp propositions with fuzzy quantifiers. Now we will discuss the last topic, and namely inference using quantified fuzzy propositions. So suppose I take two propositions, P1 and P2. There are about 10 persons in the room, and about half of the persons in the room are females. Okay. Now, given the fuzzy sets corresponding to quantifiers about 10 and about half, I can compute the truth value of P1 and P2, from the discussion we have had so far. But we want to do more, right? By looking at these two propositions, it makes sensible to say that about five persons in the room are females. Because first one tells you, the first proposition, proposition P1 tells you that there are 10 persons in the room, about 10 persons in the room. And the second proposition tells you that about half of those, about 10 persons, are females. Therefore, it is sensible to say that about five of them, about five persons in the room are females, right? In other words, we want to do inferencing from F1, from P1 and P2, we want to infer some other proposition, right? So in other words, truth value computation alone is not enough. It is very natural to expect some way to do inferencing using quantified propositions. Now, one way to do that is through something called as quantifier extension principle that Jade proposed. Okay. Now, I am not going to discuss this quantifier extension principle in general. I am only going to take one example, one type of inference scheme that follows from this QEP, namely product syllogism. Okay. You can derive another kind of inference schemes as well. We are not going to discuss that. We are only going to discuss product syllogism. Okay. So let's make our setup clear. We have two propositions, two quantified fuzzy propositions, P1 and P2. There are about 10 persons in the room, and about half of the person in the room are females. And from this, we are interested in making an inference P. And what is that inference? There are Q female persons in the room. We suspect that Q here is about 5, but we don't want to uh, uh, we don't want to jump too quickly. Let's first specify the form of the proposition that we want to infer. And this is how the inferred proposition would look like. There are q female persons in the room, where q is some appropriate fuzzy quantifier that we hope to derive from this proposition p1 and p2. Therefore, this task of inferring p from p1 and p2 is equivalent to the problem of finding this fuzzy quantifier q. Take a moment and see this. From P1 and P2, we want to derive proposition P. Proposition P is of the form there are q female persons in the room. Okay. All that is missing is this quantifier q. So our task of inferencing is equivalent to the task of finding this quantifier q. Right? So let us do that. First, analyze the fuzzy proposition P1. There are about 10 persons in the room. We can express this in its canonical form. There are q1, p1. What is q1? The quantifier about 10. And what is evens? It's a fuzzy set describing persons in the room. Notice that even in this particular set is crisp only because it describes persons in the room, which is a crisp concept. But I wanna um, um, but instead of persons in the room, you could have had young persons in the room, in which case even would have been the fuzzy set describing young persons in the room. So I wanna adopt the general terminology here, right? So that's why I'm using even is the fuzzy set describing persons in the room. Now this is the canonical form, but computationally we have seen that this behaves in this like this proposition. W1 is Q1, where W1, the variable W1 takes the scalar cardinality of E1 as value. This is something that we just discussed. Let's analyze the proposition P2. About half of the persons in the room are females, or in other words, among U's in U, among persons in the room, about half persons are females. Okay, I'm doing nothing but expressing this proposition P2 in the appropriate canonical form, which is among U's in U, Q E1s are E2s. Q is almost half the proposition, the quantifier involved in proposition P2, and even is the fuzzy set describing persons in the room, and E2 is the fuzzy set describing females in the room. Again, this is a crisp set, but I want to adopt the general terminology here. We could have had about half of the young persons in the room are overweight instead of females. So in that case, E2 would be the fuzzy set describing overweight persons in the room. And therefore, in that case, E2 would have been a fuzzy set. So I want to use the general terminology here. That's why I'm saying that E1 is the fuzzy set describing persons in the room, and E2 is the fuzzy set describing females in the room. And Q2, of course, is about half, right? And what is the truth value of this proposition? This truth value of this proposition would be Q of S1 of E1 comma E2, or in other words, this, right? So this is the canonical form of P2, but computationally, this behaves like this. W2 is Q2. And what is W2? W2 is nothing but the subset of degree of E1 in E2, or in other words, mod of E1 intersection E2 divided by E1. Now here we note that E1 is the set of the fuzzy set describing persons in the room, which is nothing but a crisp set of all persons in the room. And E2 is the set of females in the room, which is a subset of E1, right? And therefore, E1 intersection would nothing be mod of E2 divided by uh, even intersection E2 would be E2 only. And therefore, this W2 takes the value mod E2 by E1. I hope you're able to recognize that. And this is the proposition P that we want to infer. There are Q female persons in the room. Or in other words, when we translate this into the canonical form, there are Q E1 and E2s. E1 is the fuzzy set describing persons in the room, as we have just seen. E2 is the fuzzy set describing females in the room, and therefore E1 and E2 is the fuzzy set describing female persons in the room, right? This is what we have. So P is the proposition that we want to infer. Canonically, the canonical, when we translate P into canonical form, this is what we get. And what is the truth value of that proposition? It's nothing but Q of mod of E1 intersection E2. And computationally, this behaves like this. P is W is Q. And what is the value that variable W takes? It's E1 intersection E2, right? But as we have just seen that E2 is a subset of E1, and therefore this essentially is mod E2. So in other words, from P1 and P2, we want to infer P, and P1 and P2 can be expressed, and P1, P2 as well as P can be expressed in the computational form like this, where W1 is mod E1, W2 is mod E2 by E1, and W is mod E2. And we notice that W is related to W and W2 by the product operation, right? After all, mod E1 multiplied by mod E2 divided by mod E1 is nothing but mod E2. Therefore, the value that variable W takes is related to the values that variables W1 and W2 takes by the product operation. Or in other words, we can say that W is f of W1 comma W2, right? Where what is f? F of A comma B is A dot B. And what is the domain and range of f? So the first argument of f is the values of variable W1. And W1 is the computational form of a proposition of this type. There are Q evens. In other words, W1 takes scalar cardinality of fuzzy sets as value. In this particular setting, it takes the scalar cardinality of E1 as value. So the first argument of f is going to be scalar cardinality of some fuzzy set and therefore real numbers. What values variable W2 takes? W2 takes degree of subsethood as values. In this particular setting, it was degree of subsethood of E1 in E2. Therefore, the second argument of function f, which is variable W2, takes degree of subsethood as values. In other words, values from the unit interval. And it performs the product operation on these two numbers and gives some real number R. Right? So in other words, the variable W is related to variable W and W1 and W2 by this function f, where the function f is given like this. It's nothing but the product operation. But it is useful to recognize what is the domain of what is the domain of this function f, right? Now, the variables W1 and W2 are related by this function f, right? And W1 and W2 essentially occur in proposition P1 and P2 that has quantifiers Q1 and Q2. Now, Q1 is the quantifier about 10 and Q2 is quantifier about half. Q1 is modeled as a fuzzy number over the real line, or in other words, a fuzzy set over the real line. Q2 is modeled as a fuzzy number over the unit interval, or in other words, a fuzzy set over the unit interval, right? Now we know that W is related to W1 and W2 by this function, by this operation f, by this function f, namely the product operation, right? Therefore, it is natural because at the end of the day, what are we interested in finding out? We are interested in finding out Q. The whole task of inferring P from P1 and P2 is equivalent to the task of finding the quantified Q. And we have made the observation that the variable that appears in the proposition P is related to the variables that appear in proposition P1 and P2 by this function f, which is the product operation. Therefore, it is only natural to that Q should be related to Q1 and Q2 by f only. And this is precisely what quantified extension principle is. I'm not going to state it formally, but this is what quantified extension principle tells you. It tells you if the variables wi's appearing in the proposition pi's are related by some function f, then the quantifier q in the proposition to be inferred can be obtained by applying the same functional relation f on the quantifiers q1, q2, q3, so on and so forth. Right? Now the question is, how do we apply f to q1 and q2? Q1 is a fuzzy set over R and q2 is a fuzzy set over unit interval, while f is a function from R to unit interval, R cross unit interval to R. We simply perform the extension, we apply the extension principle. When we do that, we end up getting f from, sorry, when we apply extension principle to f, we lift f from R cross 0, 1 to R to this particular function. And therefore, given a Q1, a fuzzy set over R, and a E2, a fuzzy set over unit interval, I can apply F to it, this extended F that we got by applying the extension principle on this product operation. We can apply that F to it, and we can get a fuzzy set over R. Okay, so let us quickly summarize. We had propositions P1 and P2. We expressed P1 and P2 in their computational forms. W1 is Q1, W2 is Q2. We were interested in inferring the proposition P. We expressed P again in computational form. This is what we get. P1 is W1 is Q1, P2 is W2 is Q2, P is W is Q. W1 was mod E1, W2 was mod E2 by E1, W was simply mod E2. We noticed that W, the value that variable W takes, is related to the values that variables W1 and W2 take by this product operation. In other words, W can be written as f of W1 comma W2, where f is a function from R cross unit interval to R. Why R cross unit interval? Because the variable, the W1, take values as scalar cardinalities of fuzzy set. In this particular proposition, that value was mod of E1. So the variable W1 takes scalar cardinalities as values, and therefore we have R here. W2 takes degree of subsethood as values. In this particular proposition P2, that value was the degree of subsethood of E1 in E2, which turned out to be equal to mod E2 by mod E1. And therefore, we have R cross unit interval, and a product operation is performed on some real number and some number from unit interval, and that produces a number in the real number on the real line. And therefore, f is a function from R to 0, 1 to R. So if the variables W1 and W2 and W appearing in propositions P1 and P2 and P are related by function f, it is only natural to suggest that Q, which is the quantifier that appears in proposition P, should be related to quantifiers Q1 and Q2, the quantifiers appearing in propositions P1 and P2 by the same function f. And this is precisely what quantifier extension principle tells you. Now the question is, how do you apply f to Q1 and Q2? Q1 is a quantifier, it's an absolute quantifier. Therefore it is modeled by a fuzzy number over real line, or in other words, by a fuzzy set over real line. And Q2 is a relative quantifier, and therefore it's a fuzzy number over unit interval or a fuzzy set over the unit interval. And we want to apply f to it. And then we note that we can simply do that by applying extension principle to function f to lift f from this setting to this setting. So f becomes a function from fuzzy power set of R cross fuzzy power set of unit interval to fuzzy power set of R. Q1 is a fuzzy set over R. Q2 is a fuzzy set over unit interval. We apply f to it by the help of extension principle, and we get a fuzzy set over R, and that will be the Q that we want. Right? And since here our functional relationship that exists between the variable wi's and w is the product operation. This way of inferring q, q as f of q1, q2, is called as product syllogism. Why product? Because f is precisely the product operation. So I hope I gave you a sense of how to infer in the setting of quantified propositions, right? At least in this very specific setting, right? Where P1 was of the form uh, and P2 was of the form. Okay. Now let us quickly do a problem and get done with this very long discussion session. P1 is again, so the same example that we have discussed. Now about 10 and about half, these two quantifiers are to be modeled by these fuzzy numbers, and we are required to find the quantifier q. Basically, we have inferred p from p1 and p2. There are q female persons in the room, and we are required to find out the quantifier q. And we're required to find the truth value of this proposition given that there are three female persons in the room. So we have these two propositions. We quickly express them into their comp. So, okay, so P1 translates to there are Q1 evens, P2 are among U's in U, right? Right? Q1 is about half, Q2 is sorry, Q1 is about 10, Q2 is about half. E1 is the fuzzy set describing the persons in the room. E2 is a fuzzy set describing the females in the room, right? And what is the truth value of P1? If we just compute, that would be Q1 of mod of E1. And what would be the truth value of P2? That would be Q2 of degree of subsethood of E1 in E2, which is nothing but mod of E1 intersection E2 divided by mod of E1. Since E1 turns out to be a proper subset of E2, we get this. And therefore, the computational form P1 and P2 look like this. W1 is Q1 and P2 is W2 is Q2, where Q1 looks like this and Q2 looks like this. Okay. And we have inferred from P1 and P2 the proposition P. There are Q female persons in the room. And this inference is done using product syllogism. So therefore, this quantifier Q that appears in the inferred proposition P is given by applying the product operation on Q1 times Q2. And this basically is done using extension principle. So Q1 dot Q2, we make sense of this expression Q1 dot Q2 using extension principle, right? So Q1 dot Q2 is a fuzzy set over R. And what is the fuzzy set at Y? It is supremum of minimum of sorry. Remember, R is a function form. So this is how Q1 dot Q2, which is equal to Q, is given by. And this is basically what we need to compute. So you have to compute this. We have already seen the expression of how that should be computed. And Q1, we know that is about 10 and it is to be modeled like this. And Q2 is about half and it is to be modeled like this. Now, we realize that Q1 is a fuzzy number. Q2 is again a fuzzy number. And we are performing the multiplication operation, the product operation. And from the lectures on fuzzy numbers, you have already seen that whenever you take two fuzzy numbers and you perform any of the four standard operation, plus, subtract, multiplication, or division. For division, we need some more conditions, but I don't want to get into that. But for these four standard operations, performing them on two fuzzy numbers A and B again gives you a fuzzy number. And what is more interesting is that if A and B are continuous, then we have something special. We have seen that this to obtain A star B, there are two methods. There is a method based on alpha cut approach, where you first compute the alpha cut of A star B, and from that you recover A star. And then there is an extension principle approach, right? Two approaches exist to compute A star B for any of these four standard operation, or for that matter, for any operation star, right? But if A and B happen to be continuous, which is same as saying that if the membership function of A and membership function of B are continuous, then A star B, where star is one of the four standard operation, can be computed. So A star B computed via alpha cut approach is same as A star B computed via extension principle approach. Again, given two fuzzy numbers A and B and an operation star, we can perform A star B using two approaches, using alpha cut approach and using extension principle approach. Now, if A and B happen to be continuous fuzzy numbers, and this operation star is one of the four standard operation, plus, minus, multiplication, or division, then A star B, first of all, it's a continuous fuzzy number, and A star B computed via alpha cut approach is same as A star B computed via extension principle approach. And this is basically what was proved in lecture 16. Okay. So this Q, the quantifier we are interested in finding out, which was given by Q1 times Q2, and Q1 times Q2 is defined using the extension principle. In order to find Q, we can take the alpha cut approach as well, because Q1 and Q2 both are fuzzy numbers and they are continuous fuzzy numbers, right? They are nothing but triangular fuzzy numbers, and triangular fuzzy numbers are continuous. I hope that is obvious by looking just at the graph of any triangular fuzzy number. And therefore, we don't have to do these all this complicated supremum and then minimum and all that. We can adopt the alpha cut approach. Okay. So whenever your quantifiers Q1 and Q2 are nice continuous fuzzy numbers, in product syllogism, to find the quantified Q, which is given as Q1 dot Q2, you can adopt the alpha cut approach. But the justification for that follows from the fact that Q1 and Q2 are continuous. And we have a theorem that was covered in lecture 16 that tells you that when you have continuous fuzzy numbers, performing any of the four standard operations can be done in the alpha cut approach and the extension principle approach both coincide. Anyways, so we'll evaluate Q using the alpha cut approach. So this is Q1, right? So Q1 is this. So what is the equation of this thing? It's x minus 8 by 2. This is 12 minus x by 2. What is this? Okay. And therefore, for alpha in the unit interval and alpha greater than 0, what will be the alpha cut of Q1? So it would be 2 alpha plus 8, 12 minus 2 alpha. And what would be alpha of Q2? It would be uh, 2 alpha plus 3 by 10, comma 7 minus 2 alpha by 10, right? And therefore, what would be the alpha cut of Q? Now, Q is defined to be Q1 dot Q, and therefore, this is I hope you remember how to multiply two closed and bounded intervals. This was done in the first part of the course when you were taught um, arithmetic of fuzzy numbers. And maximum of exactly the same thing. Now, how to find out the minimum and maximum of these four expressions in alpha? So I took the help of graphic calculator, right? You can do that using standard calculus as well, but that would take a lot of time. So I simply choose to use a graphing calculator, Desmos. And if you do that, this is what you get. So it is obvious that for any alpha, right? So this is basically 12 minus 2 alpha, 7 minus 2 alpha by 10. And this is 2 alpha plus 8, 2 alpha plus 3 by 10. So for any alpha, green curve lies at the is the topmost curve, and the black curve is the bottommost curve. And green curve corresponds to 12 minus 2 alpha times 7 minus 2 alpha by 10, and the bottommost curve, which is the black curve, corresponds to 2 alpha plus 8 times 2 alpha plus 3 by 10. And therefore, the minimum would be this, and the maximum would be this. So in other words, which was given in this manner, turns out to be 2 alpha plus 8, 2 alpha plus 3 by 10. And now it is a matter of simplification, right? So this is nothing but, okay, so maybe I'll write the proper step. So this is 2 alpha 8 plus 2 alpha by 3 divided by 10. This is 2 alpha minus 12 divided by 2 alpha. So let us quickly expand it. What will be it? 4 alpha squared plus 6 alpha plus 16 alpha. So 6 alpha plus 6 alpha plus 16 alpha. So 22 alpha plus 24 divided by 10. Again 4 alpha square minus 14 alpha and 24 alpha. So 38 alpha plus 12 times 7, 34 divided by 10. So you can take 2 common. Uh, this is 38 by the way, and 84, so 42 divided by 5. So this is the alpha cut of the quantifier Q that we need to find out. From here, we can find the one cut, which is nothing but the set of all values, set of all real numbers that belong to Q to membership 1. And if you do that, what will you get? 2 plus 11, which is 13, 13 plus 12 is 15, which is 13 plus 12, which is 25, 25 by 5, and 2 minus 19 minus 17, minus 17 plus 14, again 25. So this is nothing but 5. And what would be the support of Q? Again, I have already indicated this in discussion session 3, if I'm not wrong. When you take the support of a fuzzy number, and when you know that you're dealing with a fuzzy number and its alpha cut look like this, so you simply take limit as alpha tends to 0 from right hand side, and you take the open interval. If you do that, you get 12 by 15, 42 by 5. So you know the support of Q, you also know the set of all values at which Q attains membership value 1. And from representation theorem of fuzzy numbers, you know that Q of X would look like this, right? It would be 1 if X is equals to 5. It would be L of X if X is between 12 by 5 and 5. It would be R of X if X is from 5 to 422 by 5 and it is 0 everywhere else, right? And you can find L of X and R of X from the fact that this is how your alpha cut look like. So when we solve, so our Q looks something like this. Suppose this is how Q looks like, and this is basically 5, and this is 12 by 5, and this is 42 by 5. And this is L of X, this is R of X, right? So when you come, and we know that the alpha cut of Q is this. So in other words, when you solve Lx equals to 5, it gives you x equals to 2 alpha squared plus 11 alpha 12 by 5. So if we want to recover Lx, we express alpha in terms of x. So 121 minus 4 times 2, 8 divided by 2a, which is 4. So 121 minus 8 times 12, which is 96. So 25 plus 40x by 4. But for any, and by the way, L of x holds between x from 12 by 5 to 5, right? But for any x between 12 by 5 and 5, minus 11 minus 25 by 40x by 4 is negative. So alpha equals to minus 11 minus root over 25 plus 40x divided by 4 is negative, but alpha is a number in this interval. It's greater than 0 and less than equal to 1. Thus, alpha is 4. And hence, L of x is, and similarly, you can compute R of x. And when you do that, you will get that it is, and therefore, your Q of x would be 1 if x equals to 5, it's L of x, but L of x is something that we just computed, and it is R of x. R of x is, and it is 0 everywhere else. And then you realize that the value of 5 of this expression and this expression is both equal to 1. Therefore, you can simplify the expression for the membership function of Q like this. And if you plot this Q, you get like this. So it attains the membership value of 5. It attains the membership value of 1 at 5. And as you go away from 5, the membership value of decreases. So semantically speaking, this is nothing but a fuzzy set that models about 5. So our quantifier, linguistically speaking, is nothing but about 5. And if you look at these two fuzzy propositions, intuitively, what is the inference that is natural to make? There are about 10 persons in the room, and about half of the persons in the room are females. So about 5 persons in the room are females. So this calculation, this machinery that we have developed so far to do inferencing using quantified proposition, this machinery that we have developed for product syllogism aligns with our intuition. And that is the beautiful part of it all. Anyways, right? And by the way, in assignment questions or even in the exam questions, you will be never asked to actually compute the membership function of Q. The most you will be asked is what is the support of Q, or for what values of X the membership of X in Q is 1. And that can be easily computed just by alpha cuts, right? So these two facts we inferred just by looking at the alpha cut of Q. But I thought that it would be a good exercise to actually evaluate the membership function of Q, just to give you a sense that this Q that we got quantifier, it models the linguistic quantifier about 5, right? But this about 5, we know that it looks something like this. But what are the exact values at which the membership becomes 0 is something that depends on the quantifiers Q1 and Q2 that are used to model about 10 and approximately 5, about 10 and about half. So the quantifiers that you use to model Q1 and Q2 determined the this value A and C. B is of course 5, right? But the meaning of this quantifier Q is about 5 only, except that the parameters A and C are determined by this Q1 and Q2. Okay. Now we are also asked that given there are 3 females in the room, what is the truth value of proposition P? So what is the truth value of proposition P? It is Q of W. Now W takes the value E1 intersection E2, but E1 is the fuzzy set describing persons in the room. E2 is the fuzzy set describing females in the room. So E1 intersection E2, which is the fuzzy set describing female persons in the room, is nothing but E2 only. And E2 is given to be 3. So we just find out the membership of 3 in Q. So 3 lies between 12 by 5 and 5, right? And therefore it would be minus 11 plus 40 times 3 plus 25 divided by 4. So minus 11 root over 145 divided by 4. And that turns out to be 0.26. So the truth value of P when truth value of P is 0.26. Okay. So with that, I conclude this session on quantified fuzzy propositions. We talked about fuzzy quantifiers, and then we talked about how fuzzy quantifiers can appear with both crisp propositions and fuzzy propositions. For both such cases, we developed canonical forms and saw how to compute the truth values. And then we also talked a little bit about inference using quantified propositions. More specifically, we talked about product syllogism. So with that, discussion session 9 is complete. I think this session resulted in 5 videos, and many of them are about 2 hours. But I hope these videos will serve as a uh, good addition to the lecture videos, right? Because these videos are much more detailed, and it will help you understand the lecture videos much more deeply. So thank you very much, and